Hola. Hi, everyone. Good morning in America. Good afternoon in Europe and Asia. My name is Sorin Micu, and as the organizer asked me, I will be the chairman of this session. I am extremely glad to be part of this anniversary workshop dedicated to a person I met 30 years ago and who played a key role in my professional development, I would say. Dear Enrique, for everything you have taught me, for the support you have given me, and for the friendship you have shown me, I thank you. And I wish you many years of good health and equally impressive scientific activity. Let me now introduce our first speaker, who is Juan Limaco from the Universidad Federal Fluminense in Brazil, a well-known researcher in control theory with impressive results, and who will present us a talk with the title Null Controllability of a Nonlinear Parabolic Equation. Please, Juan.
We don't hear you. You're on mute.
We don't hear you, Juan. Juan, we don't hear you. You have to activate. Yeah.
Yes. Yes, yes. Yes. Yes.
Yes, Juan, I listen you.
Yes.
But you need to, yeah.
Okay.
Perfect.
Thank you. Good morning, everyone, and thank you for your attendance to this special event. It's an honor for me to participate to Professor Enrique Zuazua on his 60th birthday. This work was done in collaboration with Professor Enrique Fernandez Cara, Irene Maringay, and me. One more time, thank you for your participation. In this work, we study the null controllability in dimension 2 and 3, the following model. Yg minus gradient times A of y, gradient y, equals f characteristic function of little omega with Hg belong Q, y lateral boundary, y equals 0, y initial state, y x0 equal y0x. Where A from R to R is a C3 function that poses bound derivative and 0 less than n less or equal A of R less or equal capital N. The main idea is obtained with a regular initial state y0, a regularity resolved for rho 0 b and partial derivative with respect to or rho 0 tilde b. And from this, we get more regularity from rho hat y. This allows us to estimate the following term. Gradient times of A of y, gradient y, minus A of 0, gradient y. This system on one dimension, Yg minus A partial derivative with respect to x, Ayg times Yg equal f characteristic function of little omega, with lateral boundary y equals 0, with initial state yx0 equal y0x. Definition 1. It will be fit, the one is locally null controllable, and then chi, if there exists positive epsilon, such that for any y0 belong A0, 1 of omega, and H3 of omega, with y0 nor H3 of omega less or equal epsilon, there exists control function B belong L2 of little omega times 0 chi, such that the associated state y satisfy y H equals 0 in omega. If we will say the one is globally null controllable in T if for any y0 belong A0, 1, there exists a control function belong in L2 little omega times 0 chi, such that the associated state y satisfy three this condition. Recently, important progress has been made in the controllability analysis of semi-linear parabolic equation. We refer to the work Zuazua, Fernandez Cara, Jean-Pierre Puel, Carolina Fabre, Jean-Michel Coron, and the references there. For the controllability of equation on no local terms, see work of Enrique Zuazua, Fernandez Cara, Kelly, Fernandez Cara, Silvano Meneses, and me. For systems like one, unidimensional case, per work Fernandez Cara, Tanimina, Miguel Núñez, Francielli. Consequently, it's natural to try to extend the no result to equation like one in dimension 2 and 3. The first main result is the following. Under the previous assumption on A, the nonlinear system Y is locally null controllable and anytime chi greater than 0. In other words, there exists positive epsilon such that whenever y0 belongs A0, 1 of omega, and H3 of omega, and y0 nor H3 of omega less or equal epsilon, there exists control B belong L2 little omega times 0 chi, and associated state Y satisfy three conditions if some H equals 0. The main difficulties found in the proof are the nonlinear tests appear and the main part of partial derivative operate. We will employ a technical rely on the so-called Lysternic inverse Maipan theorem in Hilbert space. Thus, in a first step, we must consider a linearized system, it's 0, y chi minus A of 0, Laplacian y, equal B, characteristic function, or little omega, plus H, with H chi belong Q, with lateral boundary y equals 0, when initial state y x0 equal y0x. We will prove the null controllability of 4. We will prove the null controllability of linearized system. The adjoint system of 4 is given by minus phi chi minus f of 0, Laplacian phi equal f1, h chi belong key, with the lateral boundary phi equals 0, phi initial state phi capital Chi equal phi chi. It's a second step we will rewrite the null controllability property of an equation for YB in a well-chosen space or submissible state control. H YB equals 0 Y0 with YB belong Y. And then we will apply the Lysternic theorem to the equation above, and will deduce the local desired result from a similar global property for the linear system 4. The following technical result due to Forsico and Emanuelovi is fundamental. Lemma 3. There exists a function alpha 0 belongs C2 of omega satisfying this property. Let us introduce the function M belong C infinite 0 chi satisfies this condition. Standard alpha 0 belongs C2 of omega and M belongs C infinito 0 chi satisfying this property. Let us set phi x chi exponential lambda alpha 0x divided by m chi. Alpha x chi equal exponential r lambda minus exponential lambda alpha 0x divided by m chi. equal alpha bar of x divided by g. Alpha bar of x, this is expression. Alpha bar of x, this is r lambda minus exponential lambda alpha 0 x. Where r greater than alpha 0 infinite norma, plus logarithm 2, where lambda greater than 0. Proposition to 1. There exists positive constant lambda 0, S0, C0, such that for any S greater or equal to 0 and lambda greater or equal lambda 0, any F belong L2 of Q, and any phi G belong L2 of omega. The associated solution to adjoint system, the solution adjoint system, satisfy this inequality. This inequality is Karl-Riemann inequality. Proposition to 1 is Karl-Riemann inequality. If we choose alpha 1 equal minimum alpha bar of x, where x belong omega bar, alpha 2 equal maximum alpha bar of x, where x belong omega bar, such that 2 alpha 1 greater than alpha 2. This condition is very important. This condition is very important in the prof main result. Then we have used to take r greater than logarithm 2 plus alpha 0 not infinite, for example. Define rho equal exponential s alpha, rho 0 equals exponential s alpha times 5 power minus 3 divided by 2. Rho 1 equal exponential s alpha times m power 5 divided by 2. And define similarity, rho tilde, rho 2, and rho hat. Remark to 1. I, exponential s alpha 1 divided by n, less than exponential s alpha, less than exponential s alpha 2 divided by n. 2i, exponential s alpha 2 divided by n, less than exponential 2 s alpha 1 divided by n. Remark 2 is very important. Remark 2 1 is consequence this condition. 2 alpha 1 greater than alpha 2. Theorem 4, linear problem, control linear problem. Assume that the function a satisfies rho 0h belong L2 of Q, rho 2 ht belong L2 of Q, a0 belong a01 of omega, then 4, linear problem, is null controllable. More precisely, for any y0 belong h3 of omega and a01 of omega, direction control B with rho tilde B belong L2 0chi a01 of omega, and a2 of omega with partial derivative with respect to rho tilde B belong L2 of Q, and associated state Y satisfying this condition. This condition is good regularity or state. Property 9. This good regularity state, Laplacian YG belong L2 of Q, rho hat square, good regularity or state. Under the hypothesis of theorem 4, rho tilde B belong L2 0chi a01 of omega and a2 of omega, and partial derivative with respect to rho tilde B belong L2 of Q. Lemma phi is good regularity of control, or good regularity of control. Proof, lemma phi. We will follow a classic argument due to Korsakoff and Imanolov. Let P0 equal W belongs C2 of K bar, such that W0 equals 0 in lateral boundary. Define it A of W tilde equal this expression. A is an inner product, and to verify this is used Karl-Riemann inequality, and can be P as completion of P0 with this inner product. Completion of this inner product. Let G of P in R defined by this expression, this continual linear form. From Lex Milgram lemma, there is only one phi belong P solution of A phi daglo tilde equal G daglo tilde. For all daglo tilde belong P. From Lex Milgram lemma, there is only one phi belong P solution this equality. Define C equal minus rho 0 power minus 2 phi, B equals C in little omega times 0 chi, Y equal minus rho power minus 2, power minus 2, L star phi. Then we have that B, I are respectively the control and associated state, the right, and they satisfy this property. Also from 10, in the property, Rothschild C equal this expression, satisfy this parabolic equation. This parabolic equation minus Rothschild partial derivative with respect to Rothschild C minus Laplacian Rothschild C equal J1 plus J2 plus J3 plus J4. Using 11 this property, control and state, satisfy this property. Using 11, J1 and J2 belong to 2 of Q. Also from estimate L star phi equal Y rho square, we obtain J3 and J4 belong L2 of Q. Belong L2 of Q. And Rothschild C satisfy parabolic equation minus Rothschild C minus partial derivative with respect to Rothschild C minus Laplacian Rothschild C equal J1 plus J2 plus J3 plus J4 and J1, J2, J3, J4 belong L2 of Q. And taking into account that Rothschild C in T equal capital T equal 0, we obtain that parabolic regularity. The parabolic regularity, Rothschild B belong L2, 0 chi, A01 of omega, and A2 of omega. With partial derivative with respect to Rothschild B belong L2 of Q. Good regularity of control. The prof lemma 5. Using lemma 5, we will prove that the solution of linear problem given by 10, the solution of problem linear satisfies good regularity. Satisfies good regularity. 9. We will use energy estimate. We will use energy estimate way rho 1 square y. Use energy estimate when rho square y chi. Use energy estimate minus rho tilde square Laplacian y. We obtain this regularity. Also, derivative, the problem 4, we get y chi minus f of 0 Laplacian y chi equal b chi, characteristic function little omega, plus h chi. And they using energy estimate with rho 2 square y chi, we obtain the regularity, and use energy estimate minus rho hat square Laplacian y chi, we obtain the regularity. The regularity Laplacian y chi belong L2 of Q, rho hat square. And finally, considering the energy estimate minus rho hat square Laplacian y chi in the original problem, we obtain this regularity. We prove good regularity of theorem 4. Of theorem 4 well proved. Proof of theorem 2. The proof of main result. Let y, f, and capital C be the function space y equals yb, satisfying this properties. These properties, if G belong L2 of Q, satisfy this property. We define Hilbert space, norm, and natural way. YB norm y square equal this property, this expression. This expression is this property and definition on y. B norm f square, this expression is definition f, definition f. And let us consider the mapping h of y in C with h yb equals yg minus gradient y gradient y minus b characteristic function of little omega y0. The theorem 2, the main result, the theorem 2, we will prove it if then equation hyb equal ay0 possesses at lot 1 solution. The theorem 2, we will prove it if that exists positive epsilon such that if hy0 belongs C and hy0 not C less than epsilon, then the equation hyb equal hy0 with yp belong capital V possesses at least one solution. In particular, this show state and control belong or space Y. Space Y. We will apply the following version of Lusternic inverse mapping theorem in infinite dimensional space. Let theorem 6, let Y and C be binary space, and let H of Y in C be a seven mapping. Assume that derivative H line of 0 from Y in C is onto, and the X is W inverse to the right of H. Theorem 6 is theorem the inverse to the right of H. H of W C equals C. To applying theorem 6 in theorem 2, applying several lemmas. The proof of the lemmas 7, 8, 9 are very technical and use big calculation that we will give a brief idea to demonstrate them. Lemma 7. Let H of Y in C be the mapping defined by 24. 24. Well defined. Since A is Lipschitz continuous, HYB norm C square less or equal I1 plus I2 plus I3 plus I4 plus I5 plus I6. 6 terms. Definition of espacio Y, I2 plus I1 plus I2 plus I5 less or equal 6 YB not Y square. Now analyze term I3 and I4, which are the most difficult. I3 of I4 the most difficult term. Since A is C1 and globally Lipschitz continuous, H3 less or equal K1 plus K2. And N less or equal 3, and N is less or equal 3, then A2 of omega contained in L infinito. One has K1 less or equal this expression. This expression is finite by good regularity, or state of problem linear. Good regularity or state. Good regularity at 9 or state theorem 4. Analogous to less or equal this expression. This expression is finite, good property of theorem 4, linear problem. Also, one has I4 less or equal L1 plus L2 plus L3 plus L4 and L2 less or equal this expression. This expression is finite by the good regularity of state of theorem linear. L2 less or equal this expression, B calculation, L3 of L4. Lemma 8. The mapping H of Y in C is continuously differentiable to prove lemma 8 is using theorem 4, good regularity or state, and using denominate convergence theorem levels. Using theorem 4, linear problem, good regularity or state, and theorem dominate convergence theorem levels. I am going to pass to next slide. Let H be the mapping defined by 24. Then H line 0, 0 belong L capital Y in capital C is on. Fear notice that H line 0, 0 Y line B line equals Y G line minus A0 Laplacian Y line minus B line characteristic function of beta omega Y line is 0. Consequently, H line 0, 0 is only if and only if for each H Y0 belongs C. The rest is YB belong capital Y satisfying this equation. This equation is a linear problem. Hence, the existence for YB with this property is ensured by theorem 2. This shows that A line 0, 0 is surjective. And this ends the proof on lemma 5. Finally, applying theorem 6 using lemma 7, H well-defined and continuous, using lemma 8, H según mapping, and using lemma 9, H line of 0 is on. Consequently, from theorem 6, theorem 2 is well proven. Thank you very much. This is the ending of my presentation. Thank you so much for your attention.
Thank you very much, Juan, for this presentation, which probably delighted Carleman specialists. Please, if you have questions or remarks concerning the presentation, you can use the raise hand button, which is below the main window. Are there any questions? Yes, please, Enrique.
So thank you, Juan. Gracias, Juan, por tu presentación. Thank you for the interesting talk. In your opinion, Juan, what are the most important open questions in this area that has been so fertile in the last, say, 20 years or so?
Yes, so this problem, this problem change y by gradient y is this important problem. For global control, a global inverse function theorem will have to be used, but we will have to solve linear problems with variable coefficient in a space such as being independent of two coefficients. That's very complicated.
Thank you. I see.
Thank you, Juan. Thank you, Enrique. Is there any other question? I have a question, please. I remarked that you use initial data in H3. Is that correct? The initial data you control. You suppose that your initial data is in H3. Is this true? At the very beginning, I saw.
H3 with sufficient large capital T. We also have exact control in zero. We let the solution become small, and then we apply the local result. For H3 initial state important.
Okay, thank you. Is there any other question? If not, thank you again very much, Juan, for this presentation.
Thank you very much.
We pass to the second speaker of this section. He does not need any or not much presentation. Giuseppe Butazzo from Università di Pisa, a well-known researcher, top researcher in calculus of variation and optimization. Giuseppe will present us a talk with the title Variations on a Team by Chigger. I hope I said it well. Please, Giuseppe.
Okay, can you hear me?
Yes, we hear.
Let me use the full screen. Okay, thanks, Doreen, for the presentation. And let me say that it's a very great pleasure to be here, even if only virtually. I would have preferred to be in presence, but this is life. And thanks to Carlos and to all the organizers for the very nice idea they had to honor Enrique. So I was trying to remember when we met first, Enrique. So I was unable to find the date, a precise date, but surely it should be something like 20-25 years ago. And in the most recent years, the contact with Enrique became more strict because we started in 2005, I guess. 2005, we started to organize together this meeting in Benasque. At the beginning, the meeting was relatively small, 30-40 people, but it was extremely successful. And in the last editions, we reached 150, 160 people. After a while, at the beginning, Enrique and me were alone as the organizers. After a while, Olivier Glass joined us and Günther Leugering also. So now we play in quartet. And I should say that most of the success of these Benasque workshops are due to the energy of Enrique. So the place is wonderful. The scientific center is really very, very nice, but the energy of Enrique was fundamental in the success of the meet. We did already 8 editions, and unfortunately we canceled the 2021, but simply we postponed in 2022. And hopefully this will take place in this very nice place. So let me pass to the scientific presentation. These variations on a theme by Chigger. So what is the theme by Chigger? So let me say that this is a joint work with Luca Briani, who is a student of my PhD student in Pisa, and Francesca Prinari, who was a student of mine, and she is now back at the University of Pisa. The starting point is this celebrated Chigger inequality in the 70s. He found this inequality in the 70s. And the inequality is very simple. The inequality states that if you take this ratio, the square root of the first eigenvalue, lambda is the first eigenvalue of the Laplace operator, lambda of omega, first eigenvalue of the Laplace operator with Dirichlet boundary condition. So if you take the square root of the principal eigenvalue divided by what he called the Chigger constant, this ratio is always bigger than 1/2, no matter what the domain omega is. This ratio is always bigger than 1/2. So what is the Chigger constant, h of omega? The definition is rather simple. The Chigger constant, h of omega, is the infimum of the ratio perimeter over measure when the set E runs among all the subsets of omega. So you have omega, you take all the subsets of omega, take the ratio perimeter over measure, and the infimum of this number is the Chigger constant of omega. And so the Chigger inequality is very interesting because it relies a spectral quantity like the principal eigenvalue to a geometrical quantity as the Chigger constant. So this ratio is always bigger than 1/2. So now many questions arise. I should say that this domain is extremely rich. A lot of interesting open questions. So I will try to give you a hint on how to solve some of them, but most of the questions are still open. First, the inequality above is not sharp. And many questions arise. What is the right sharp constant? 1/2 seems too low. What is the sharp constant instead of 1/2? So this constant should depend on the dimension, and nobody knows what is the right one. Second, existence of optimal domains. Is it true that this ratio has a minimum or a maximum in some sense? Then generalization to other situations. I will speak about this generalization. And what happens if you, instead of taking all possible domains, you restrict the class of domains by adding some geometrical constraints. So you see many questions, and I will try to comment some of them. I should say that this field has been considered by several people. The one I found on the literature is the work of Elias Thuy, who is now in Erlangen. An interesting preprint on HAL. HAL is the French version of the archives. This is restricted to the case of convex domains. And also Enea Parini worked on this field. Enea is the Université de Marseille. And he wrote a nice paper on journal convex analysis in 2017, still on convex domains in R2. The proof is very simple. The proof of the Chigger inequality is extremely simple. Actually, it is simply a smart use of the Hölder inequality. In fact, the Chigger constant h of omega can be estimated from above by this ratio gradient of v over v, where you take v, the square of the first eigenfunction for the Laplace operator. If you take the square of the first eigenfunction, you see it's very simple. A simple Hölder inequality gives you that h is less than twice the square root of lambda. More generally, I want to consider the principal eigenvalue for the P Laplacian, not only for a desire of generality, but you will see how important is the P. So the range of situations which occur modifying the P is very large, and this is what I want to discuss. So lambda P is very easy to define. Is like in the case of the usual Laplacian, is the minimum of the Rayleigh quotient gradient u power p divided by integral u power p, and u runs in W1P0 of omega. So this is the principal eigenvalue of the P Laplacian. When P equal to 1, this is very well known, that when P is equal to 1, this lambda P, lambda with index P equal 1, is exactly the Chigger constant h of omega. And so the natural generalization of the Chigger inequality is that one that you see on the middle of the screen, lambda p power 1 over p divided by lambda q power 1 over q is larger or equal to q over p. Q is smaller than p. The classical Chigger case was p equal 2. In fact, you have the square root of lambda divided by h, and h is exactly the eigenvalue when q is equal to 1. So you see that this is the most natural generalization of the Chigger inequality. So again, this can be proved very easily by a smart use of the Hölder inequality. Equivalently, you may multiply, divide by q, and then you can rephrase this inequality by saying that the p times lambda p power 1 over p is an increasing function, is equivalent to the inequality above. But again, the question about the sharpness of the constant q over p arises. So let me also discussed the extremal case p equal 1 and p equal infinity. So p equal 1, as I said, the lambda p power 1 over p when p goes to 1 gives the Cheeger constant h. On the contrary, when p goes to plus infinity, lambda p power 1 over p tends to one of the in radius. What is called the in radius is the maximal radius of a ball contained into omega. So when p is very large, you approach the reciprocal of the in radius. So let us define this functional. You see here, fpq of omega. So fpq of omega is just the ratio I said above. So lambda p power 1 over p divided by lambda q power 1 over q. Remember that q is less than p. So this functional, the shape functional fpq. And let us define small m is the infimum of this functional, while big M is the supremum. So there are two different optimization problems. The infimum, I want to minimize the ratio FPQ, and I want also to maximize the ratio FPQ. And by now I consider the class of all possible domains without any geometrical restriction. So in this sense, the Cheeger inequality can be reformulated by saying that the small m pq is bigger than q over p. And here I want to stress the dependence on the dimension d. You see the index d stands for the dimension of the ambient space. This is a very important parameter, the dimension. So the easiest case is in, well, this always happens. The easiest case is the one-dimensional case. In this one-dimensional case, due to the fact that all open sets are union of disjoint intervals, in this case, the functional FPQ is constant. And this constant can be also computed explicitly, is the ratio pi p over pi q, where this pi p is has this expression 2 pi p minus 1 power 1 over p and divided by p sine pi over p. If you put some particular choices for the exponent p, you will find that pi 1 is equal to 2, pi 2 is the usual number pi, and pi infinity is equal to 2. You can see the plot of this pi p as a function of p. You see the maximal value is the usual number pi, which occurs for p equal 2. For p equal 1, the corresponding number is 2. And for p very large, this pi p tends to 2 again. So the easiest case is the supremal value. The supremal value, capital M. So for capital M, we have a complete answer, well, almost complete answer. In fact, from now on, I take the dimension bigger or equal to 2, because the case of dimension 1 is trivial, as I said. The theorem is the following. This number, capital M, is non-decreasing with respect to the dimension D. And this is what happens. This supremal value is plus infinity for all q less than or equal to the dimension while it is finite when the number q is strictly bigger to the dimension. It would be very interesting to characterize the value capital M when it is finite. So when the q is strictly bigger than the dimension. We do not know, it should be quite difficult problem, I guess. How do we obtain this theorem? So in the case q less than the dimension, maximizing sequence, so a sequence such that the value of the function goes to plus infinity, is obtained by doing a fine perforation of the unit ball, as you see in this picture. So here you must be extremely careful in tuning the radius of the perforation in terms of the distance between the closed perforations. So the right way to tune the radius in terms of the distance depends on the dimension. This is what people call the Cioranesco-Murat example. So working on a generalization of this Cioranesco-Murat example, you can show that if you are below the dimension, so if q is below the dimension, the ratio goes to plus infinity. So this solves the problem M equal plus infinity, the supremum is plus infinity. On the contrary, if the q is strictly bigger than d, in dimension d, due to the fact that points have a positive capacity, this number m is finite. And then the question arises what this number is. We can prove it is finite, we can give some not sharp bound, but the characterization is an open question. In the two-dimensional case, a reasonable conjecture could be it would be interesting to prove or disprove this conjecture, but just in two-dimensional case, that a maximizing sequence is made by removing from the unit disk the centers of an hexagonal tiling, like in this picture you see. So take the unit disk, we are in R2, and remove from this disk the points, the black points you see on the screen. And these black points are the centers of an hexagonal tiling. This we believe this should be a maximizing sequence. And on this sequence, we may compute explicitly the value. In higher dimension, the situation is much more delicate, because this is linked to the famous problems of optimal packaging, for which very little is known in higher dimensions. And now let us pass to the infimum, small m. Small m is the infimum of the functional given by the ratio I introduced above. So we know from the Chigger-like inequality that this infimum, small m, is larger or equal to q over p. And we said that this inequality is not sharp. Why it is not sharp? Because we can prove the following facts. First, this number, small m, the infimum, decreases with the dimension. So going up on the dimension will decrease this infimum, the infimum number. And second, when the dimension is very big, tends to infinity, the ratio provided by Chigger is actually sharp, but only for the dimension tending to plus infinity. Now, if you put together these two facts, that Q over P, which is the number provided by Chigger, is obtained asymptotically when the dimension is very large, and that this infimum is decreasing, you see well that for a given dimension, the Q over P is not sharp. So is only asymptotically sharp for a very large dimensions. It would be very interesting now to prove or disprove, if you want, the existence of optimal domains, omega PQ. Optimal in the sense that they minimize the ratio FPQ on the class of all domains. There are some hints, some hints in favor of the existence. The hints are that drilling holes in that case is not efficient, because drilling holes will increase the ratio FPQ. So the intuition says that you don't have to drill holes, but when you don't drill holes, this give a kind of extra compactness. So a good conjecture could be that optimal domains for the minimum, for the small m, they should actually exist. In the case P equal infinity and Q equal 1, we have this ratio F infinity 1 is simply the reciprocal of in radius times the Chigger constant. And in this case, we can compute the infimum, which is 1 over dimension, 1 over d, while the supremum is plus infinity. And the minimum is given by any ball, and the supremum by finally perforated domains. So you see in this case, the minimum exists and it is a ball. Now, it is also interesting to consider admissible sets, admissible domains, with some geometrical restriction. And here we consider the convexity, which is a very strong geometrical restriction. So we consider this class AD convex, which are the domains in RD, which are convex. And we put a bar just to distinguish. So small m with a bar on the top means that we are doing the infimum, but on the class of convex domains. And similarly, the capital M with the bar on the top means that we are taking the supremum, but only on convex domains. Again, when P equal infinity, the values of these two extremal numbers, small m bar and capital M bar, can be easily computed. And we find that the infimum is given by the ball, is 1 over this lambda q of a ball, for any q, I mean. While the supremum, the capital M, is given by 2 divided by this pi q number. So you see in this case, both of them are finite. The minimum is given by any ball, while the supremum is given by a sequence of thin slabs. What is a thin slab is a d-dimensional domain times the interval 0 epsilon. This is like a thin plate. So in this case, if we add the convexity constraint, these numbers are finite. So the plus infinity now disappears. So you see again, the plus infinity was possible before in the class of all domains due to the fact that perforations were possible. Now, with the geometrical constraint of convexity, perforations are not anymore possible. And this is why this number, capital M bar, is always finite. And these are two bounds. From the left, Q over P, a maximum with pi P over D times pi Q. And from the right is pi P times minimum of Q over 2 and D over pi Q. And these inequalities follow by smart use of Hirsch-Protter inequality that you see here, linking the in radius with the eigenvalue, and the Boozer inequality, linking the eigenvalue with the Chigger constant. And now again, for the easiest case is the case of the supremum. We don't have the proof, but a very reasonable conjecture is that the supremum, so the capital M bar, the supremum over the family of convex domains, should be pi P over pi Q, which means that maximizing sequences of convex domains are made by thin slabs. This is true when Q equal 1, but we believe this should be true for any P and Q. This is for the supremum. So you see, the supremum can be at least easily conjectured, not proved, but easily conjectured. What about the infimum? The infimum is much more delicate. Is much more delicate. Okay, let's see the two-dimensional case. This is easier. The two-dimensional case is easier. In fact, we can prove that if Q is less than 2 and P is bigger than 2, P was the numerator and Q the denominator. In this case, we can prove the existence of a convex minimizer for FPQ. How the proof works? By contradiction, assume this is not true. If this is not true, this means that a minimizing sequence should be made by thin domains. And for thin domains, we know, because we are in dimension 2. Dimension 2 is crucial here in this proof. Then we know that FPQ tends to the ratio pi P over pi Q. And then it is enough to produce a domain such that we are strictly below. And this can be done by taking the unit square. Here in this proof, the dimension 2 is really crucial. For instance, in dimension 3, we can't repeat this argument. And this works only when the dimension 2, not only, and also when Q is less than 2 and P is bigger than 2. On the contrary, it is reasonable to expect the existence of convex minimizers for any FPQ, for any P, any Q, any dimension. Still, even if we remain in the classical Chigger case, the classical Chigger case was P equal 2 and Q equal 1. In this case, in dimension 2, we know the existence. In dimension 3, nobody knows. Of course, we expect that an optimal domain should exist for the class, even for the classical Cheeger ratio. We are rather close to the proof, but unfortunately there is a small step which looks very difficult. So the theorem is the following: if the mapping from D into this infinite value m sub D is strictly decreasing, then we can prove the existence of an optimal domain. But unfortunately, we can only prove that this map is weakly decreasing. In English, we say non-increasing. So as soon as we have the strict monotonicity, this would quite easily imply the existence of an optimal domain. So as I said, even for the original Cheeger case, this is not known in dimension 3. There is a very interesting conjecture by Enea Parini that in dimension 2, we know that omega optimal exists. So Enea Parini claims that this optimal domain in dimension 2 should be a square, just a square. And in this case, we may compute the explicit value of this m bar 2, which is 1.17 and so on. So if the Parini conjecture is true, this would imply the existence of an optimal domain in R3. You see, a conjecture in R2 implies the existence of an optimal domain in R3, just because of the theorem I showed about the strict monotonicity. And so let me finish by collecting some open questions that I already mentioned in my presentation. It is nice to see the open questions all together. So first, characterize this the supremum, capital M, when Q and P are bigger than the dimension. Otherwise, this is plus infinity. At least in dimension 2, I would be happy to see at least in dimension 2. In higher dimension, it should be extremely difficult. Second, exists. So for the supremum, we do not expect the existence of an optimizer. On the contrary, we expect the existence of optimizers for the minimum on the class of all domains. So this is a very interesting question. The question about the strict monotonicity in the class of convex domains is also an open question. And this implies, once you prove the strict monotonicity, this implies the existence of optimal minimizing domains. Then, concerning the supremum on the convex sets, the expectation is that maximizing sequences are made by thin slabs, and which gives that the supremum is pi p over pi q. Then the Parini conjecture that optimal domains for the minimum in the two-dimensional case is a square, and this provides automatically the existence of a minimal domain, convex domain in R3. So I can conclude by wishing happy birthday to Enrique.
Thank you, Giuseppe. let's open the question session. Are there any question, remarks on the talk of Giuseppe? Yes, Rajeh.
Hi. Once again, greetings to Enrique and thanks to Giuseppe for the excellent talk. I heard a talk of yours sometime back, maybe in another seminar. I was wondering whether it has relation, some of these to the Blaschke-Santalo diagrams and meaning just a curiosity kind of.
Hi Rajesh, nice to see you.
Yeah,
You are right. You are right. Yeah, the Blaschke-Santalo is a further step, even more delicate, because Blaschke-Santalo, when you are able to draw the full Blaschke-Santalo diagram, this is much more than an optimization question. So here I was limited to present the minimal and maximal values. Of course, there are all the other cases in which you want to describe the Blaschke-Santalo diagram. Sure. This will be an even more difficult question. Sure.
thank you. And I would like a copy of your
Sure. I will
presentation. Yes.
I will send you.
I missed the start because it was supposed to start at 9:50 and it started a little bit early, I guess. Sorry.
Yes, we are ahead of the schedule a little bit. The next question, Enrique, please.
Yeah, thank you, Giuseppe. So what is the original motivation of this Chigger constant? So it's like the Rayleigh quotient for p equal 1, right?
Exactly. This is exactly the Rayleigh quotient for p equal 1, indeed.
But why, I mean, for the Rayleigh quotient, there is a clear motivation, is the Laplacian, the eigenfunctions, and well, all PDE somehow make use of that. But for Chigger, what is the motivation?
I think the Chigger motivation was geometrical. In fact, the Chigger inequality, I think the original Chigger paper was in the much larger framework of Riemannian surfaces, where you can do exactly the same. But actually, the Chigger constant itself is exactly like the Rayleigh quotient. You take the Rayleigh quotient for the P Laplacian. So if instead of the usual Laplacian, you take the P Laplacian with P small close to 1, and you get exactly the Chigger constant, which has a more geometrical meaning. I mean, the spectral meaning we know very well, the eigenvalues, the spectrum. The Chigger constant can be defined just in terms of purely geometrical quantities. And this was, I think, the motivation by Chigger.
And then the classical symmetrization techniques to show that the circle, the disk is optimal for
the circle
for
is
lambda
optimal.
1
Yes,
applies to Chigger as well,
absolutely. Yeah.
I see.
On the contrary,
okay.
let me say why the Parini conjecture is very reasonable. Take the ratio square root of lambda over h, okay? If you take a smooth, so the domain, the optimal domain, we know it exists, cannot be smooth, by sure, cannot be smooth. Because if you have a smooth domain and you add a small corner, the small corner has no effect on the Chigger constant, while this decreases a little bit the eigenvalue. We know that if you increase the domain, the eigenvalues decrease, the usual eigenvalues. On the contrary, adding a small corner has no effect for the Chigger constant. So this shows that optimal domains cannot be smooth. And this is why Parini conjectured it should be a square.
So why adding a corner doesn't change the Chigger constant?
Yeah, because there is an explicit way to compute the Chigger constant in a planar domain, in a planar convex domain. You look at the curvature. You see the curvature until the curvature enters into a corner, and then it stops a little bit before touching the corner. So this means that the last part of the corner has no effect on the Chigger constant. So you see, if the domain is smooth, you can add, by taking two tangents, you can add the small corner, and this is much better than the smooth domain.
Mm-hmm.
But numerically, it seems that the square is the right one. Parini computed the ratio for regular polygons, and for regular polygons, actually the square wins.
Mm-hmm.
Is a good hint.
Mm-hmm. And if the domain is non-convex?
No, if the domain is non-convex, well, I don't know. I don't know because, well, as I said, the perforations are not efficient. So first you should prove the existence of an optimal domain, which is not clear.
But for instance, non-convex, but how you say, simply connected. I mean, like a non-convex polygon. What does it do, the Chigger constant, when you make this square to be non-convex by maybe making one of the sides to be concave?
Yeah, I see. I don't know. I can't guess. It's a very difficult. It's a very difficult ambient to guess answers.
Okay, very interesting. Thank you, Giuseppe.
Thank you. Rajesh, do you have another question?
Yeah, maybe a short question, but
yes,
it can
please.
be for later. I also think that maybe there should be some connections. I remember some of your works where some of these things are related to transport, optimal transport kind of questions. So is there connections to optimal transport in this kind of thing, and can take from there be used?
I don't see a direct connection. Well, there are a connection optimal transport with some other shape optimization problems, but in this case, I can't see a direct connection. If
but
you find one, it would be very
no,
nice.
but I mean to say that the P going to infinity or one kind of case usually has some like formulation, at least some old work of yours with.
Yeah, the strong links between mass transport and shape optimization are in the case when you do some mass optimization. So you distribute mass inside the domain. But in this case, there is a constraint that a domain should be a domain. You don't distribute mass inside. So the characteristic function remain characteristic function and not mass densities.
Yeah, and one more question. So how much of like quantitative isoperimetric inequalities help in answering some of these issues?
This is a very interesting question. In fact, this could be one of the tools that could help in this series of open problems, I said. Well, the quantitative estimates had very strong developments in the last years. So we have now quantitative inequalities for the perimeter, quantitative inequalities for the eigenvalue, and these are very powerful tools. This could be one the methods to attack the questions. Yeah.
Thank you.
Thank you. I have a curiosity also. In the case, in one-dimensional case, does the inequality have any sense?
Well, in the one-dimensional case, everything is constant. The ratio is constant, so and no surprise. So
what would be the perimeter of a segment?
The number two, the
okay.
two extreme, two. The perimeter is just the two because you have two extreme points.
Yeah.
So
well,
this makes the problem a bit trivial.
So if there are not, Rajesh, you have another question? I see.
No, I didn't lower my arms. No, I don't have further questions. Yeah.
Okay. Well, if there are not any, I see one more hand of Axel, but I'm not sure if it's the hand for a question. Probably not.
Yeah.
Yes. Yeah, it's a question.
Yes.
Okay.
It's a question.
Your hand is of different color. I was
no, it's not true.
At least in my computer, I was not sure is the same. Yes, please, Axel. Sorry.
No, just the connection with the graph theory, in the sense that I was reading that there's interpretation of this constant as the conductance on a graph. And my question was if you are working also in graphs.
Yeah, I know that the Chigger constant have been studied a lot from people in graph theory, but we did not exploit this side. But I know that there is an enormous literature about Chigger constant and graph theory. You are right. Yeah.
Okay.
No, we
so maybe there should be some interesting links there.
Sure, by sure.
Okay. Yeah. Thank you. Thank you.
Thank you, Axel. And if there are not any more questions, let's thank again Giuseppe for these very interesting questions and answers.
Thank you.
Okay. I see a lot of hands, right? Maybe. Okay, let's pass to the following speaker in this afternoon session or morning session. And it is a pleasure for me to introduce Luz de Teresa from Universidad Nacional Autónoma de Mexico. Lucero was one of my colleagues during the PhD thesis in Madrid. I think she was the first full PhD student of Enrique. To my knowledge, it is so. Please, Lucero.
Well, thank you very much, Sorin. Nice seeing you. And happy birthday, Enrique. So I will start with some memories. So this is more or less 3 years after I meet Enrique. So maybe I can, so here is Enrique. He was very young. And there you can see Sorin. So Sorin is here, I think. And here is Carlos Conca. Okay. Here, no, Carlos?
Yes.
Yes.
I also have this picture.
Okay. And here is me.
93.
Okay, so this is something to recall. And here I have another photo of more or less the same time. Maybe it's 1 year before in Santander. I don't know. So here is Enrique again. And here is me. And I don't see if I recognize them. Okay, so Bresis and I don't know.
Luis Vasquez.
Yes. Juan Luis Vasquez, but I don't know if Sorin was here or Carlos or, right, maybe not. Maybe it was before Sorin arrived to Spain, maybe.
I missed this one, yeah.
Yes, yes, I think so. Okay, so just to preserve memories, as Enrique Fernandez Cara says yesterday. Okay, so I start now. So I'm going to talk about a hierarchic control problem. So this kind of problems arise in the field of game theory. So it's a very long date problem. So in this kind of problems, you have a first player that is called a leader that does a movement. And then you have a second player that reacts to the first movement of the leader and tries to win or to optimize the response to the leader movement. So this is in general the kind of problem you want to work on. And the historical papers due to von Neumann and Morgenstern in 1943 and Nash in 1915 were very, very important in this field. And here you have the von Neumann paper, but the introduction, and here the full Nash paper. So this is the paper of John Nash. That was very, very important, and what is now known as Nash equilibria, in fact, was not due to Nash, okay? It was before Nash. Okay, so there are several concepts that are around this game theory problem. And when you have two players, you have, or controls, now I'm going to start with control theory, but when you have two players, you have one leader and one follower. This is called a Stackelberg strategy. And then you have a lot of concepts related with this problem when you have several players. So you may have a Nash equilibria, a Pareto strategy, etc. But I will only focus on Stackelberg strategy, okay? So I'm going to work here with the heat equation. So in 1994, Ragliglions presented this problem. So you have a heat equation, linear heat equation, and you're acting with two controls on this equation. So here you have an H and a V that have different objectives. So you have two controls with different objectives. So one of them wants to optimize a functional. So the target of V is to minimize this functional. So here you have several things. You have a target function. So you want to be close. So my solution Y wants to be close to this YD. And you have this beta that is important in the procedure you will use after, but you only want to optimize this functional, okay? On the other hand, you want H to reach a state, so you want a controllability objective for the control H that may be a null controllability objective, okay? So I'm going to present the para-even way of do that. So here is the control objective. So you want to minimize the temperature of the beers, okay? So you put some ice on it, but also you want to open the bottles, okay? So here you have this small part where you open the bottles. So this is the control region 2. This is the controllability objective. And the ice is the other control objective that optimize the function. Okay, so this is a way of seeing these two objectives control problem. Okay, to be serious now. So we want the traditional setting is the following one. You have the leader control, so the first player is going to be H. So H wants to achieve a controllability objective. So Y of t equal to 0, or an approximate controllability objective, something like that. And the follower control, V wants to achieve given H. So the leader has made a movement, so has done something. And we want this follower control to minimize a given functional. So it has an optimization target. So how to solve the problem? So first, you have to fix the leader, okay? And then try to optimize, to obtain a minimum for this functional. Since the functional is continuous, strictly convex, and coercive, you have a unique minimizer, and you can characterize this minimizer as the solution in my control region O, the corresponding to V, okay, of a solution at the adjoint of the heat equation. So here is the adjoint, starting in 0. So this is a backward heat equation, so you start from capital T, but that has a right-hand side precisely the solution of the controlled equation with the H, and you have also this objective YD that appears here and is in the region where you're trying to get close to YD, okay? So this is the way you can characterize this minimizer, okay? So once you have characterized this minimizer, so you are working with two coupled equations. So they are coupled. So Y appears here, that is the solution to the first equation. And then you have P that appears here, that is the solution to the second equation. So they are strongly coupled equations. One is backward, and one is forward, okay? So the first results about this kind of problems were due to Jacques Lyons in '94, and he proved that this system is approximately controllable. That means that they can do Y of capital T less or equal than epsilon for every epsilon, working with this coupled system. Okay, so in fact, it's approximately controllable to 0. So only they want to get close enough to 0. Okay, and very recently, like 6 years ago, Ararun and Fernandez-Cara and the team there proved that when the control region, so omega small omega is a control leader, is a control region for the leader control. So they can prove that when this OD, so the target region, let's say, and the leader control region has non-empty intersection, it is possible to drive the solution of the first equation, that is the one that is important for us. You don't want to do anything to P. P is only a characterization of the optimal control. So you don't want to do anything to this equation, even if they are coupled. Okay, so they can drive the solution to 0 of Y. So you have this leader control is doing its job. If you have a growing condition on your target YD. So this growing condition is appears because of Kahneman inequality. So in fact, this rho square is related to Kahneman inequalities. So you can control a heat equation with a right-hand side if this right-hand side goes exponentially to 0 as t goes to capital T. Okay, this is a kind of condition related with controlling a heat equation with a right-hand side. Okay, so they prove that this problem is not controllable. Okay, so how to solve this problem? So you have to prove an observability inequality for the adjoint to my coupled system. So now we have to work with this system. Okay, so you have to work with the adjoint to the system. And the adjoint to the system is here. It's again one equation backward that corresponds to Y, and one equation forward that corresponds to P. Okay, so this is the adjoint. And as is known, you have to prove an observability inequality. And in this situation, the observability inequality you need to prove is this one. So you want to observe phi at 0, okay, and theta with some weight here in front of theta by observing it from the control leader region and in time 0t, okay? So you want to prove this observability inequality, and to prove this observability inequality, at least Araruna et al. Prove it using Kahneman inequalities, and the fact, two things that are very important is that theta at 0 is 0, okay? This is very important to prove the inequality, and also that you can choose beta to be large enough. So this, you have beta as a parameter in your equation. So recall that beta was part of the functional I wanted to minimize, okay? So this was the parameter you wanted to minimize. So once you prove the observability inequality, you can define as the leader control to be H equal to phi hat, where phi hat is the solution to my adjoint system that minimizes this functional, okay? So here you can see that you have the target YD that was in the minimizer problem, and is multiplied, no, sorry. And it is multiplied by theta, and that's why you need the inverse of the weight. So here you have rho minus 2, and I have rho square here. Okay, so they are compensating in Helder inequality or Young inequality. However, no, they are compensated the weights, one with YD and the other with theta. Okay, so the problem was solved in this situation, and there are several works related with hierarchical control. For example, for heat and wave equation, Lyons in '94, ocean circulation models, Stokes, moving domains, and in general, all of these problems were had an approximate controllability objective for the controllability problem, and they minimize the minimizer objective was the classical one, and the other one was the approximate controllability for the control objective. Then Araruna, Fernandez-Cara, and Santos work with linear and semi-linear parabolic equations, and they prove control to trajectories. Also, Araruna, Meneses, and Rojas Medar work with micropolar fluids, but they get an approximate controllability result. And I have some results with Victor Hernandez Santamaria on coupled parabolic equations, and also some results with Cristian Montoya for Stokes systems. Okay, so now what I'm going to present is a new result with Enrique Fernandez-Cara, Bianca Calzavara, and Jose Antonio Villa. And the thing is that we change the roles of the target of the leader and the target of the follower. Okay, so it's like with the beer. We wanted to consider like as a secondary functional, so the one related to the follower. So we are going to minimize something, okay? But the idea is to drive the solution to 0, but with the follower. So the weights that appear here will guarantee that y at capital T is equal to 0. And we want the V, the leader control, to minimize a functional. So when you revert the objectives of the follower and leader control, to solve the problem is very different. Okay, so first, given V, that is my leader control, I want to obtain a follower control that drives the solution to 0. So now the follower wants to drive the solution to 0, okay? So we need to work in weighted spaces, because we know from classical controllability results for the heat equation that if you want to control a heat equation with a right-hand side, that now is going to be this V, that is the leader control, you need V to decay exponentially to 0, okay, at time capital T. So we are going to work with weighted Sobolev spaces, and these weights, ρ0, rho, and ρ0 here, are related with Karleman inequalities. So what do you want to do? So you have a leader control, and you associate to each leader in this space. You want to find a follower control. So V is given, you want to obtain F that depends on V, that minimizes functional, but in fact, the objective is not to minimize. This is only a technique, okay? In fact, what you want to obtain is drive to the solution to 0 at capital T. So the objective of the follower is y of capital T equal to 0, okay? And then we look for admissible control, so the optimizers of my functional, primary functional. So you will have an optimizer of the primary functional, but of course, once you move this control, you will have a different follower control. So you will have admissible control that satisfies that this primary functional on V hat and in F of V hat is going to minimize this function, okay? So, as I said before, the weight functions are related with Karleman inequalities. I think that almost all of you have heard of Karleman inequalities, even if you don't know how to prove them, but you have some weights that depends on the control region, and here is the dependence on the control region. So you have this eta 0 that has no critical points outside the control region omega, and you construct using this eta 0 some weights. So here are the weights, and the interesting point here is that you are dividing by a function that depends on t, and in fact this function vanishes at capital T. Okay, so this is the key points in the weights. So you have these weights, and I am going to use these weights to solve my follower control. Okay, so the main result I am going to present here is the following one. So if we consider the linear system with A in L infinity and Y dot in L2, then for every leader control V, so given this V in this weighted space, you have exactly one function, f of V, that minimizes the secondary control objective. And if you set P tilde of V to be the solution the functional that depends on V and F of V, then you have only exactly one minimizer of this primary functional in U, and consequently, you have one associated follower. So it's like a structure scaled that you have to use. So to prove this problem, as Juan Limaco proved this morning, he solved a 4-order partial differential equation using Carleman inequalities. So in fact, we do something like that. So we defined LA of y is the parabolic equation forward, and the adjoint is the backward parabolic equation. You work on a space P dot that are continuous functions that vanish on the boundary, C2 continuous C2 functions in omega times 0t, and there you can define a symmetric and bilinear form that is related to Carleman inequalities. So you define this symmetric and bilinear form on P0, and in view of the Carleman inequality, you can prove that in fact the symmetric bilinear form is a norm. Okay, so you can induce a norm using this bilinear form, because this is your Carleman inequality. So this, here you have all the weights that appear before, and you can see that this in fact induces a norm. So you can complete the space using this norm. So you work on the completion of P dot with the norm induced by the Carleman inequality. And then given a leader control in my weighted space, you can find exactly one solution using Lax-Milgram theorem, and the f of v is precisely given by this related to the solution of my Lax-Milgram problem. Okay, so in fact here you have this plus that equal to vp prime and y dot p prime 0. Okay, so this is just a solution to a Lax-Milgram problem. Okay, and in fact you can construct y, the solution to the original problem, as rho minus 2 the adjoint equation to P. So y is going to be given in this way. Okay, so this is how you prove it. So just Lax-Milgram, as I said before, and then you get that. Okay, so now you have this function that as for v you get the primary functional that you want to minimize, and you can see that it is well defined, C1, and strictly convex on U, and therefore you get a minimizing control of this primary functional. So this minimizer is has can be characterized as the solution of the following optimality system. So you will have f of v hat again as before, y hat to be like that, so as before. And now it's much more complicated because v hat has to solve to be like that, is given like that, where psi hat solves also a 4-order problem. So when I put here an m of p prime psi hat, you have this 4-order problem that I put before, and it is solving this problem with phi hat here. Okay, so you have like a chain of solving problems. Okay, so in this way we can reverse the roles of the leader and of the follower. What happens if you want to solve a semilinear problem? So when you have a semilinear problem, we are going to have much more difficulties to solve this hierarchic control problem. Again, you can consider your secondary functional, okay, and your main functional. And now we lose the convexity of the functionals S and P, okay, because of this nonlinearity. So the way we can act is to solve the, or to linearize, to solve the problems. So we linearize, okay, and we solve for each z in L2 of Q, we solve the hierarchic control problem, okay? And in fact, this is why we need, or at least this is the technique we were able to put in practice, okay? We need to minimize the functional to characterize the optimal, not the optimal, but the control problem, the one that drives the solution to 0, okay? We did it minimizing a functional, the secondary functional, because when we want to obtain the fixed point, you need to, in some way, construct this null controllability problem associated with the follower control, okay? And in this way, we're able to construct a minimizing sequence and then obtain the fixed point for the result. So what we did is find a follower in the nonlinear situation, and you have to work on this set where you have a pair F, VF, so V is the leader, F as the follower, and F belongs to the followers of V. So given V, you have F, okay? And you can see that you have a coercive and sequentially weakly lower semi-continuous functional to this pair. And you can get a minimizer in G that gives the solution to our problem. So when you modify the roles, you get a much more difficult problem. So we also solve a multi-objective problem with Pareto equilibria. We work also with a distributive control leader plus a boundary control follower. So here things get more complicated because you have some boundary control follower. So the one to drive the solution precisely to zero from an optimizer control leader that is minimizing dysfunctional. And then we are finishing now with Jose Antonio Villa, with my student, a problem with both controls on the boundary. And there you need so compactness results. And in fact, we work with the leader control in H1/2, 1/4 of the boundary on this kind of results with fractional Sobolev spaces are required to obtain the good control results. And also we are working with this modifying the roles of the leader and the follower with the wave equation. And there are, I think, a lot of problems, open problems, working with other equations that have to be solved. Okay, so I know here is not. Thank you very much to all of you. And I finish with happy birthday, Enrique. So the most important thing is the teorema. Okay, so here is a bottle of wine I found in Spain that is called teorema. So it's not a, it's like that. You find it in the wine shops. Okay, so thank you.
Thank you, Lucero. Please keep the bottle until our next meeting.
Okay.
So are there any questions, remarks? Please.
So actually I have a question for Lucero. This picture in Santander, can you show it again?
Yes.
I was trying to figure out.
Wait. Okay, let me share my screen.
Yeah, so there is to the right, there is you mark myself, then there is Tomeu. Tomeu is the chairman of our department in mathematics in Madrid now. Then there is Beziz, then there is Juan Luis Vázquez.
Yes.
And behind Juan Luis Vázquez, there is Ireneo Peral, who unfortunately passed away this winter.
Here, no?
A colleague and friend from Autónoma de Madrid for many years.
Yes.
That unfortunately will not be with us this in this edition. So yeah, and then the person next to Juan Luis is George Papanikolaou.
I don't know. Don't remember.
I think it's George Papanikolaou,
Yes,
right? The guy with
you
the
are
bear.
right. Yes,
Yeah.
it is Papanikolaou.
And then the next one is Madalena, right? Madalena is the wife of Ireneo, right? And I think the next one is Paul V, right? Is he Paul V?
No, I don't know. I
don't
don't
know.
remember.
Paul
I was
V,
very
right?
young.
The guy who, well, I mean, he did many things, but in particular, he has, these celebrated papers in traveling wave solutions, Five and MacLeod, and so. and then the next one just before you is Fernando Quiroz. Okay, yeah, but I mean, I was curious whether Ireneo was there, and yes, Ireneo is just behind Juan Luis and George Papanikolaou. So yeah, good, thank you. And then if you go back to the previous picture in Almeria, so this was actually, you see in Almeria there was next to me to the right there is Christodoulou, right? Christodoulou was at that time in Princeton, and it was just that summer, maybe 93, I think it was in the summer 93, that that Wiles, you know, announced the proof of Fermat theorem, right? And then Christodoulou was shocked, right? Because he said, well, this guy has been sitting in the office next to mine for years without talking to anyone. Nobody knew what he was doing. And then, you know, suddenly this summer he opens the door and says, oh, I got the proof of Fermat's theorem, right? Yeah. Okay, yeah, so that was 93. And probably as you said, Santander was a bit earlier, right? Yeah.
I think it was
okay.
the year before, yes.
Okay, so thank you, Lucero, for all these many years of friendship and support and collaboration and enthusiasm and good work that has led to, well, such a now rich family, right? Thank you.
Thank you.
All the best for Chema too, right?
Yes, thank you.
Are there any other questions?
Just an observation. So it happens
Yes,
to
please.
be Carlos' birthday, so many happy returns, many feliz cumpleaños, Carlos, also.
Thank you very much, Rakesh.
Also, we have your anniversary today.
Yes.
Felicidades.
Hombre, felicidades. Qué casualidad.
Very thanks.
Muy bien, muy bien.
Happy anniversary.
Feliz cumpleaños, Carlos.
Muchas gracias.
I would like to ask Lucero if the relative position of the two supports is important in this problem. I remember that in sensitive problems, it was a big deal how the supports are related, if they intersect or not, and so on.
Yes,
is in this situation the same problem?
Yes, we have the same thing, but now the important set is the OD, where you have this target objective, YD. So you have to have non-empty intersection with this set, where you, with the control, you want to drive exactly to zero, no, the solution, or to approximate controllability. No, it's related with this set. But
is it necessary?
The follower control and the leader control cannot have an intersection, because you cannot act on, it's not natural to think that you can act on the set where the leader is acting and then you modify the behavior of the leader. So in fact, they have they have empty intersection, the control leader set and the follower set have empty intersection between them. But then you have this condition of non-empty intersection between the control to zero and the set you have the control. So this is related to the optimization problem. You have these two equations, okay?
Any other question?
Axel,
yeah.
Raising his hand.
Axel, yes, please, Axel.
See, in this context of Stackenberg equilibrium, etc., Kahneman inequalities are giving some insight about numerical methods in the sense of trying to obtain global minima in this minimization step. I don't know if my question is understanding.
I think that we have with Victor Hernandez Santamaria and Frank Valle some results, numerical results for insensitizing controls that are not exactly the same kind of equations that you have to solve. Because when you have an insensitizing control, you don't have this strong coupling, okay? So as you see, when you obtain this coupling of the result by Araruna, I had these two equations. Maybe I can share again my screen, sorry. It's talking with hands in mathematics is very difficult, no? Okay, so you have, no, it's blocked. Okay, no, not here. So here, okay, you have these two equations. When you have the leader control that drives the solution to 0 and the follower control that solves some optimization problem. So this is the not my result with Enrique Fernandez Cara and Bianca and Jose Antonio, but the result of Araruna or Fagner with Enrique and Mauricio. So in their result, they have to solve a null controllability problem for this system, okay? So you have this heat equation coupled with this one. So it's like you have a strong coupling because P appears in the equation of Y and Y appears in the coupling of P, in the equation of P. So it's a strong coupling. When you work with insensitizing controls, you don't have this term. And of course, you don't have YD, but YD may be 0, okay? So for insensitizing control, we have some numerical results with Frank Boyer and Victor Hernandez Santamaria. And there we can solve with the weights and all that. So it's related with Kahneman weights and that. We can solve this problem of driving, in fact, P to 0 at 0, that is related with, as I said before, insensitizing control problems. But here, I don't know what to do with numerics. I am not an expert in numerics, so maybe young people or numerical experts can do something about that.
Okay, thanks.
Thank you.
Thank you. Are there any other questions? Well, if not, let's thank again Lucero for the nice presentation.
Thank you.
And now I think we have a break. Of course, these breaks are not so nice as it were when we were together, but that's the situation. So we have a break until 11:40, I think. Yeah, so about 25 minutes.
Okay.
See you.
See you.
See you.
See you. Qué gusto verte, Sorín. Un abrazo.
Igualmente.
Te llamo luego por WhatsApp.
Vale, de acuerdo. Hello again to everyone. Our second part of the first session will begin now. And it is a pleasure for me to introduce my friend Marius Tuxnac. I think he does not need much presentation. Let me just say that he is from the Université de Bordeaux in France, and he will present us presentation with the title Reachable Spaces for Infinite Dimensional Systems. Please, Marius. We do not hear you yet. Maybe
Marius, it seems that you are muted.
Do you hear me now?
Yes, we hear you now.
Okay, thank you. Sorry for that.
Where are you, Marius? In the space station? Where are you?
Exactly. I'm very far.
Yeah, okay. Yeah.
So let me share my screen. And then put it in full screen. Okay, so it's a big pleasure for me to have the opportunity of giving a talk in this anniversary conference. So I am certainly one of those which met Enrique the longest time ago with Carlos, Sorin, and Lucero. So this was exactly 30 years ago when he visited Orléans, where I was working for my PhD. And since then, our collaboration and friendship was a very impressive one for me and extremely useful. I could took a lot of advantage of the fact that if you want to understand, for instance, something which is known maybe by some, but badly written in the literature, you should ask Enrique, and then you will have a quick and deep understanding of the subject. So our research directions went in sometimes in different directions, but then they joined again, and I hope to have still a long time the opportunity of working with Enrique. If this meeting were not virtual, what could you do? We could offer Enrique a nice suite like this one. This was one of our common adventures when he became honoris causa of the University of Lorraine. As the other guy, which is today 60, which is Carlos, which has this honor several years before. And then another activity remarkable with Enrique is sports. But here, in fact, it's a place where which he made me visit to do mathematics behind, the idea being how to generate a wave which is appropriate for surfers in an artificial basin, which here is somewhere in Basque Country in a marvelous place. So all these are very nice memories with Enrique, and which are both essentially for science, but also for sports, as I could recently see when he made me bike 40 kilometers in Erlangen. Okay, let me now go to the outline of my talk. I will speak about a subject which concerns the heat equation and its perturbations. The first result stated in the way I will make precise a bit after goes back to Fattorini and Russell. So roughly speaking, the question was having a dynamical system, a linear one, with a control, which are all the states you can reach at a given time. In fact, this is a very important problem already in finite dimensional system theory, which is simple for linear system, but very complicated for nonlinear ones. For systems described by partial differential equations, Fattorini and Russell were the first to ask this question, and the progress in this field was very slow, and only 3-4 years ago, some new methods have been proposed, which reached to very nice results. The focus in my talk will be on the robustness of the reachable space with respect to perturbations of the generator. And as a subsequent result, the robustness of the property of null controllability. I will make the context more precise later, but what I would like already to say, that something which is known in infinite dimensional systems, so for PDEs, is that in the case of exact controllability, if you do, for instance, small perturbations of the generator, you will preserve the exact controllability property. The same thing holds if you have a kind of compact perturbations, which is a so-called compactness uniqueness theorem, which Enrique was one of the very first to systematically apply to systems described by PDEs. So I will discuss this in a quite abstract setting and a surprisingly simple one. And then I will come back to the applications for the heat equations, and namely to the relation with some results of the two Enriques on a heat equation perturbed by non-local terms. Let me try to motivate the problem. So we have a system, very classical one, Z dot is equal to AZ plus BU. Of course, A and B can be matrices. This is a classical finite dimensional situations, but we are more interested in the case where the state space capital X is infinite dimensional. When the input space U is finite or infinite dimensional, and when A generates a semigroup T of strongly continuous semigroups of operators on the state X, the operator B may be bounded or not. Unbounded means that it goes in a larger space, which corresponds to the case of boundary control if we think to a PDE system. Now, the solutions, it's well known, right, using the variation of constants formula or the Duhamel formula as the semigroup TT applied to the initial state Z of 0 plus an operator which I denote by phi TU, which is nothing else but the convolution of the semigroup with the control term BU. So here U is the input function, Z, the function Z is the state trajectory. There is a condition of admissibility, which roughly speaking says that the values of phi t's, instead of being in X minus 1, which is for granted because of the property of B, lie in a smaller space X. If this holds, we say that our control operator is admissible. It's obviously true if B is bounded, so if it's in values in X. Otherwise, it requires extra assumptions. For instance, the framework which will appear later on in this talk is when A is a negative operator and the operator B is not too unbounded. So it's a bit unbounded, but by the degree of unboundedness does not is not larger than 1/2. Now this space may be very complicated, even for simple examples. What one should say, that unlike infinite dimensions, in generally it depends on tau and it is not a closed subspace of X. I didn't write here what it is this space in finite dimension. Infinite dimensions is nothing else but the range of the Kalman matrix. It's exactly the range of the Kalman matrix, so it does not depend on time. It's of course a closed subspace. What is generally true is that this space is becomes a Hilbert space when it is endowed with a norm transported from L2 of 0 tau capital U. So it's a very simple functional analytic result. So it is a Hilbert space with an inner product and a norm, which are not very very explicit, of course, because they are defined by this transport procedure. Now, for general system, we cannot say general infinite dimensional system. I mean, we cannot say a lot of things about the reachable space. This is why we need more assumptions on our systems. And these assumptions are generally connected to the controllability properties. So here we have the main three of them, which is exact controllability, which means that the operator phi tau, which is a convolution operator, is onto. We have null controllability, which says can be described in two manners. The usual way is to say that for every initial state, Z0, you can find a control such that Z of tau is equal to 0. And an equivalent way is to say that the range of the input operator phi tau contains the range of the semigroup. This is easily seen from this formula. Having Z of tau is equal to 0 is solving the equation capital T index tau Z0 plus phi tau U is equal to 0, which can always be done provided that the range of phi tau contains the range of T tau. These three concepts coincide with the usual controllability when our systems are finite dimensionals. Now, some first set of remarks. In the finite dimensional case, all linear time invariant systems can be seen as controllable ones. Why? Because it suffices to restrict them to the reachable space. It's a closed space, it's invariant for the operator, and of course, it's also invariant for the input operator, and then our system becomes exactly controllable. This reachable space coincides with a range of states obtained with signals which are very smooth. So if I restrict myself, for instance, to controls which are analytic in time, the reachable space will be the same, again, only in the finite dimensional case. Okay, but of course, exact controllability is a very rare property in infinite dimensional systems. And it is easily checked. We can again take an example, for instance, from the paper of Sorin and of Enrique on the heat equation on a half space, that when we restrict the operator to the range of phi tau, the system to the range of phi tau, we do not obtain in general an exactly controllable system. So a good example for that, a quite pathological one, but which is an example for that, is the heat equation on a half line. Now, I try to come to the main object of my talk, which is the robustness of the reachable space with respect to perturbation of the generators. So, as I mentioned, or I did not yet mention, even in finite dimensions, if I take an arbitrary system and if I make a small perturbation of the generator, the reachable space may change. Arbitrarily small perturbation of the operator. Why? Because I remind to you that the range, the reachable space is the range of the Kalman matrix. And if you think to the Kalman, the formula of the Kalman matrix, changing a bit matrix A, the matrix A will change the range, with the exception of the case where the system is exactly controllable. Of course, in this case, the range will be the whole space, and since maps which are on to form an open set in the set of all continuous maps, then linear maps, then I will have robustness. So we have robustness of controllability for finite dimensions, but we do not have robustness of a reachable space. This robustness of the controllability property holds also in infinite dimensional, provided that by controllability we mean exact controllability. So exact controllability is robust with respect to small perturbations. This is a result formally written by Ad, which is basically a very simple one. So the basic question which I'm interested in is, can this robustness be extended for systems which have weaker controllability properties? For instance, a result which is not available in the literature is, if I have a null controllable system, I take a small perturbation of the operator, of the generator, is null controllability preserved? This is something which has never been studied to my knowledge, or I don't know if studied, but there are no results on this subject. Coming back to the exact controllability property, this is a very convenient one because it also allows quite easily to pass from the linearized problem to the nonlinear one by a simple fixed procedure. When I say simple fixed procedure, it's just controlling with a source term f, which is arbitrary, and then doing a fixed point. We know that the similar procedure for the null controllability, namely for heat type equation, does not work, unlike we make very special assumptions on the source term small f. The notion of reachable space is intimately connected with the notion of null controllability. The first connection, which goes back to Fattorini and Zeidman, is that for a system which is controllable in any time, is null controllable. So null controllable in any time, the range of phi tau, so the reachable space, does not depend on time. So that's a first important property. This is the departure point of considering the systems which are null controllable in arbitrarily small time as a good category of systems to be studied as far as reachable spaces are concerned. We can also, once we have this, the proof is remarkably simple. I give a very simple one in a recent paper with Hellet and Normand, but essentially it's just rephrasing the very nice proof of Zeidman. I will not repeat it here, but once we have this proof, it is easily seen that the norms of range of phi tau and range of phi tau prime for every tau and tau prime positive are equivalent, is just a consequence of the closed graph theorem. So now for such a system, we have an object which is called the reachable space and which does not depend on time. The problem when we want to apply this to PDEs is that we would like to know exactly what this space is, and we will see that this is much more complicated. Oh, so I'm too far. Okay. Now I will state our main perturbation results. So for the moment, I don't know what it is, range of phi tau, because I'm in a completely abstract setting. However, I would like to say which are the smallness condition on the perturbation or other conditions which allow me to have robustness of the reachable space with respect to perturbation. The first one is small perturbations, which is expected. But what does small mean here? We don't claim that this result is sharp, but I think it's really not far of that. The resulting theorem 1 says that for systems which are null controllable in any time, the reachable spaces are invariant with respect to perturbation which are small in this norm. So this space range of phi tau, we will see later on examples, is generally a very small space with respect to the state space. So if the state space will be L2, we will see later that this space range of phi tau will be a space of analytic functions, at least for the heat equation. And so we need an operator P acting smoothly on very smooth functions and having small norm. Then the reachable space is preserved. The second type of perturbation applies to systems which are more particular. So I have here a negative generator, which immediately makes you think at the heat equation. So it's self-adjoint and negative, of course. And then I have some technical conditions, but roughly speaking, the important one is that the perturbation operator P sends a kind of fractional Sobolev space, again in range of phi tau. So in this second theorem, my perturbation operator is moving. X1 minus alpha minus epsilon will be a Sobolev type phasing applications, and it is mapped on a space which is much more regular in general, a space of analytic functions. Then, if this happens, and if I had the kind of how-to conditions for every complex number S, the kernel of S identity minus I minus P star cap, the kernel of B star is reduced to 0, then we have again the invariance of the reachable space and also the invariance of the null controllability property. This second theorem is a kind of abstract version, slightly improved, of the result of Enrique Fernandez-Cara and Enrique Zuazua on a heat equations perturbed by a non-local operator. This example will appear in a slightly different form on my forthcoming slides. So these are the two main perturbations results. But when writing this paper, well, I didn't mention the authors, but I should have mentioned it somewhere. These are joint results with Sylvain Hervé-Doza and Kevin Lebalch. When writing this paper, which is already on HAN, we realized that in fact the main result was extremely simple, and it was a kind of regularity theorem. So if I have a system which is well posed in a classical sense, null controllable in any positive time, and I take the restriction of the semigroup to the reachable space, which I know it doesn't depend on time, no? I know it doesn't depend. I obtain a new system. But what is important to do to continue the analysis would be to say that the restriction of the semigroup to this range, to this reachable space here, still is a C0 semigroup. The fact that it's a semigroup is obvious. This follows from the null controllability property. But why is it a C0 with respect to the very strong topology of range of phi tau? And this is really the main result. We give a positive answer to this question. And automatically for this class of system, we have a positive answer to the question I was asking at the very beginning of my lecture. If I restrict systems which are null controllable in any time to their reachable space, then I obtain an exactly controllable system. So if I take the heat equation with boundary control and I restrict it to its reachable space, I have really an exactly controllable system in the most strict sense possible. So in fact, maybe I will not insist too much on the proof. I have 2 slides with the proof of it, but I'll try to avoid the technicalities. I will just say that to do that, it suffices to show that the semigroup with respect to this norm is bounded for small t. And once we have shown this, which is done really completely on the 2 slides which I wrote here, and so it's not very complicated, but it's a very, let's say, tricky proof. Once we have done this, there is a result of Hille, which says that for a semigroup on a Hilbert space, which is bounded for small t, we have that the semigroup is strongly continuous. So boundedness implies strong continuity, in fact, for on reflexive Banach spaces. It's not generally true for a Banach space, but for reflexive Banach spaces, so for Hilbert ones, this holds. So this is the whole proof on these 2 slides. If I really have time and if you are interested, I will come back at the end. Now, let us see what can I get for the heat equation. Of course, even for a simple system like the one I will write here, it's 1D with Neumann boundary control. The basic question is, what is the reachable space? Because my assumptions on the perturbations are in terms of the reachable space. So if I want to perturb this heat equation with something, the condition on the perturbation will be expressed in terms of the reachable space. So let us take this very simple example. So I have a heat equation in 1D with Neumann boundary control at both ends. So I'm on the interval 0 pi, and I have the controls U0 and U pi at the 2 ends. So my operator will be the generator will be the Neumann Laplacian, and the control operator will be the combination of these 2 Dirac masses. So in fact, it's not really correct. What it is here is not the sum. It's a vector, minus U0, U0, U pi, delta pi. So it is known from Fattorini and Russell that this system is null controllable in any time. So the first requirement to apply our theory is fulfilled. The second one would be to know what the reachable space is. And here, happily, we know not for a very long time. So the exact characterization of this space has been obtained in the last 2 years in a sequence of papers, finishing with this paper of Harman and Orsoni in 2021, where they showed that it's what's called a Bergman space, a Bergman type space. So I have here my segment 0 pi. A priori, the reachable states are functions defined on 0 pi. How can I characterize them? There are functions which can be extended to holomorphic function in this red square, and which have the properties that they are in the Sobolev space W1D. So they are, or H1, if you prefer, H1 of this square. So it's holomorphic with the function and its derivatives, partial derivatives, which are square integrable on D. And so this is an inequality. This is an inequality which improves what has been shown, for instance, by Rosier and co-authors, that the reachable space contains the functions which are holomorphic in some larger disk, or if we go back to Fattorini and Russell, which have shown that the reachable space includes those functions which are holomorphic in a whole strip like this. So here we know what is a reachable space, and now how can we apply our abstract results to this situation? First, we can consider small potentials. So it's exactly the previous system. I add P of x times Z of Tx. And now, if I consider this potential holomorphic on D, so it may be singular, but far from the interval 0 pi. And with the norm in W1 infinity of D small enough, then the reachable space will not be affected. So that's a first result, which is strongly improving the only perturbation result of this type which was known, which was the result of Rosier and Laurent, which asked again holomorphy in a much larger set. Then another class of perturbation, and here I come very close to the paper of the two Enriques. I take again my heat equation and I add a non-local perturbation with a kernel K, which is holomorphic in D with respect to one of the variables and the L2 with respect to the other one, roughly speaking. That's all what we ask. So with a unique continuation property, so this, if you remark here, it's a kind of Hautus test. We also assume that this holds. Generically, this holds, but we have counterexample where it is not true for boundary control. Then we obtain again that the reachable space and the null controllability property are robust with respect to this kind of perturbation. So remark that here there is no smallness assumption. It's just regularity plus unique continuation. In the paper of the two Enriques, this unique continuation property was not specifically supposed because they were doing internal control and with stronger assumptions on the kernel, so it was automatically satisfied. So there are many other examples which you can do with this methodology. Linear equations in several space dimensions. Internal controls, again, even in several space dimensions, and also non-linearities. With non-linearities, our result will be, of course, local. So the invariant space will be invariant, but I would say a small ball of the reachable space will be invariant with respect to non-linear perturbations. So to conclude, interesting results in the same directions can be obtained by taking controls which are very smooth functions. So we can characterize the reachable space with very smooth functions, and this can be very useful for nonlinear problems, as has been shown in particular in the first talk of Juan Limaco today, but with a very different methodology. There are connections also with the famous problem of the control cost. Estimating the norm on these Berman spaces could give very good information on the control cost. And finally, let me just mention that the extension I evoked to several space dimensions are based on a recent result of Strohmeyer and Waters, which gives quite precise information, not a characterization, but very precise information on the reachable space for the multidimensional heat equation with Dirichlet boundary control on the whole boundary. So that's a preliminary step to obtain generalizations of the presented results in several space dimensions. And that's what we have partially done in the recent paper with Hervé Doza and Le Balc. So I think that my time is over. I would like again to wish the best to Enrique, both at the personal and professional level, and hope to have more and more interactions with him in the years to come. Thank you very much.
Thank you, Marius, for this very interesting presentation. Now we open the session of questions. There are several people already raising their hands. Let me see. Yes, Enrique, please.
Okay, thank you, Marius. Merci beaucoup. Yeah, Marius is a very old friend, right? So we met when? It was early
91.
90s. 91, the same time as Sorin, actually. Yeah. Yeah. Okay, good. So, yeah, regards also to Zina, Marius.
Thank you very much.
Yeah. I mean, in the sports section, you didn't show your photos in Roland Garros, right? Yeah.
Yeah. No.
Okay, next time.
I'm only cycling now. That's my new passion.
Yeah. I mean, you have to get trained to come to Erlangen again. I mean, yeah. It's unacceptable that you find Nuremberg too far to buy, right? So yeah, I mean, yeah. Next time we have to get to Frankfurt or to Munich or to Bayreuth or minimum, right? Okay, good.
Of course.
So yeah. To which extent does your result apply if you replace the Laplacian by a variable coefficient Laplacian, just depending on x, right? Smooth coefficients depending on x. Is the same?
We don't know anything. Already an analytic potential, it's completely new. So
why is that hard? Why? What is the key point to deal with an analytic potential, for instance, depending only on x?
For the heat equation, we use the explicit formula of the solution with a Gaussian and the image method. So for the heat equation without any perturbation, the proof is based on the explicit formula on the Gaussian. This domain D comes from the Gaussian effect. If you look, it's really connected to the Gaussian. And then all what we have done here is to try to perturb it. But if you perturb the principal in the principal term, it would be more.
So, but do you expect? But I think you mentioned something in your talk, right? So, if you add a lower order analytic potential, do you expect this phase space where the control semigroup evolves? You expect it to change with respect to the potential, or in some sense, if the analyticity of the potential is sufficient, you expect everything to flow in the same space as for the heat equation?
I expect it to lie in the same space if it is analytic in the domain D, and we prove it, but only if it is small. If it's analytic and small with respect to the N infinity norm, we prove it. But we are unable, we are not far, but we were not able to prove that it's still true for an arbitrary analytic potential.
So you could do a small perturbations which are analytic, right? This is what you can do.
You can do, and also some perturbations which are non-local, as in your paper, which don't need to be small. But,
yeah, this is what Enrique said yesterday. Yeah.
Yeah.
I see. And okay. And this is also in several dimensions, what you are saying now, or only in 1D?
This works, let's say that in several space dimensions, we don't know, yes, we have results also in several space dimensions, but they are very precise only if the control acts in the whole neighborhood of the boundary. Because it's the only case where we know exactly what the reachable space is. In general, we do not know.
Yeah, then you can use the green function, the Gaussian everywhere, right? But if you have an arc of the boundary, I understand.
So we have some results also with an arbitrary control region, but then the constraints on the kernel are stronger. On the kernel, they are stronger.
And you also mentioned our result with Sorin, right? Saying that in the half space you lose controllability. Does this methodology bring any light when you look to growing domains that in which you indeed expect the controllability to be lost eventually, or?
Well, this methodology, I don't know about growing domains, but in exactly your situation, it gives quite simply the proof that the fact that the reachable space intersecting with the range of the semigroup is reduced to 0. You can prove it with using the explicit Gaussians again, that the intersection is 0. So of course you have no hope. So because controllability would mean the reachable space containing the range of the semigroup. So they are.
Yeah, but it would be nice to see how this arises when you highlight a domain, right? So how things scale so that the space shrinks to 0.
I think we can say something, but we didn't try. Yeah, we might say, because everything is very explicit indeed. you can construct something very, very explicitly. Yeah.
Okay, when you come back from the space station to Bordeaux, you can continue this, right?
Of course.
Thank you.
Okay, thank you.
Thank you. Any other question? Yes, Jean-Michel, please.
Yes, it's out of the scope of your talk, but I was wondering what is known for the robustness of the null controllability. Is it possible?
For the null control, for the perturbation?
Yes, for perturbation. What is known?
As I mentioned, not much. As I mentioned, for our second theorem, which is with regularizing perturbations. So for the heat equation, it would be non-local.
Yeah.
Also holds for null controllability.
Oh.
So here this is true. For small perturbations, very strangely, even in this very strong norm, we don't know how to prove that null controllability is robust. So,
for example,
which is true.
If you consider the example with the kernel K, the interval from 0 to pi K, and if you have the Otus criteria, it's not sufficient to get the null controllability.
No.
There are counterexamples.
Yeah, clear. So how to test for heat equations? There are works, but you don't have a necessary and sufficient conditions. You have sufficient conditions, but which are quite strong, which have been obtained, among others, I think, by Camille Laurent and also by Pierre Ricci, I think. So there are people which have worked on how to test for null controllability, but there is not necessary and sufficient condition like for the wave equation. Okay. For the wave type equations, we have a necessary and sufficient condition for exact controllability, but nothing like that for
the equation and null controllability.
Already, somehow our result can be seen as a how-to test for a class of parabolic equations. So because we say if we have the how-to conditions and some other assumptions, which are a lot of them, then we have null controllability in particular. So this is, in fact, we can also interpret our result as a how-to test, but there are many others, but only sufficient conditions.
Thank you. Thank you. Very nice talk. Very interesting.
Okay. Thank you. Any other question? Enrique, your hand is still raised.
Oh. May I a question? Yes. The Peru, from Milton Cortez from Peru. May I?
Yes, please.
Okay, just one. Okay, yes. In spite of the high dimension, you can to study on the non-cylindrical domain. It's possible about that one? The non-cylindrical domain.
Not with these methods, no. In fact, to be more precise, in several space dimensions, we have good information on the reachable space only for a ball. So we don't even have it in any geometry.
Right, because I had to know about the knowledge, the Hume method, Hilbert unit method. Maybe it was possible to study with the non-cylindrical domain. Well,
I think yes, but that's completely different. Yeah, I think because what's called the Hume method is just the functional analytic argument. It's right. Of course you can apply it, but at the end of the day, you need to check some conditions, some inequalities, and that depends on your problem. And moreover, this doesn't, let's say, concern the same question. The controllability is, I wouldn't say, it's a different question. Most of the time, easier than the reachable space. Okay, so because the final information is just that the range of the operator, of the input operator, contains the range of the semigroup. Here, you want to say exactly what is the range of the input operator.
Okay. Thank you, Professor. Thank you very much, Professor.
Welcome.
Thank you. Any other question? If not, let's thank again Marius for his interesting presentation and his answers.
Thank you very much. Thanks a lot.
This session is now finished. My role as a chairman is finished, but let me thank all the speakers from today for their effort and for their interesting presentations. And also let's thank the organizer for their great job. Thank you and see you soon.
Thank you, Sorin. Gracias.
Bye-bye.
So now we have a break for 1 hour or so, right?
Yes.
Yes.
At what time do we start?
And 1 hour and 4 minutes.
Okay, so 5:30 here in Europe. Okay, okay.
Yes.
So have a good lunch. Good.
Bye-bye.
Thank you.
See you.
Some important
See you very
information,
soon.
if you can see the chat, please stay at the end of today, because we have a free space that we will use this time so in like a social dinner. So we don't have the opportunity to drink some wine and beer, but it's for soon. Okay.
Okay, see you.
See you. Ando con el viejito, con el... No,
Okay. Hola, Sebastián. Hello.
Hello, Alberto. How are you?
Fine, thanks. So we are on time. When you wish, we can start.
1 minute.
Okay, 1 minute. The speaker is there, no, Emmanuel?
Yes.
Hello.
Yes, I'm there. I'm there. Can you
Okay.
hear me?
Yeah, perfectly.
Yes.
Great.
Okay, so I will introduce you. I will present you. Cuando me digas, Sebastián.
Adelante, profesor.
We can start now. Okay, so. Okay. Good afternoon to all. I am very happy to be here. I will be the chairman of this afternoon or evening session of this great conference in honor of Enrique. So very welcome all of you. I will take this opportunity, just some moments to say congratulations to Enrique for his inspiring scientific career. That has been very important to this community, in particular for young people in Latin America. So I wish you an excellent continuation of your career, Enrique. So we are on time, so we will pass to our first speaker of this session. Okay, so just a few words. Emmanuel Trela, he is a professor at Sorbonne University in Paris and is the director of Laboratoire Jacques-Louis Lyons. During the last decade, he has developed an amount of research together with Enrique. He has co-authored more than 20 articles and proceedings with Enrique Zuazua. We will talk about exponential convergence towards consensus for non-symmetric linear first-order systems in finite and finite dimensions. So, Emmanuel, are you ready?
I'm ready. Can you see my slide?
Yes, we see your slide now, and
okay.
The pointer. So go ahead. Thank you.
Okay. Thank you very much. Thank you very much. Happy birthday, Enrique. We indeed have quite many articles together. But today, so I will not present an article that was done with Enrique, but rather with Laurent Boudin and Francesco Salvarani. I think, by the way, that Francesco is in the room. Are you there, Francesco?
Yes, I am.
Okay.
Good afternoon to everybody.
Hi, Francesco. So our work, as you can see, the title is a bit long, but it is about consensus systems that are also very familiar to Enrique, who wrote a number of papers also on consensus systems. But here, our main objective is to be able to treat in an L2 way, I will explain what I mean here, non-symmetric systems, non-symmetric consensus systems. So let me immediately come to the mathematical model that we have in mind, which is this very famous model that was designed quite long time ago by Exelman and Krause, which is for the moment in finite dimension, this very simple system. So you take capital N agent, whose position, say, for instance, is modeled by this state variable, yi at time t, which evolves according to this differential equation. So as you can see, yi dot is equal to the sum over all possible agents of a coefficient sigma ij, which is an interaction coefficient, times yj minus yi. So sigma ij is a kind of interaction of the agent number I with the agent number j. And the state of the agent I can also be, for instance, an opinion. And indeed, in what we worked together with Laurent and Francesco, this is the opinion model that we have in mind. Let me recall that for this kind of system, we say that we have consensus whenever all the state variables coincide. So when all, for all I and j, you have yi equal to yj, which is equal to some y bar. So y bar is also the average of all agents, right? And when you have consensus, of course, you have an equilibrium of the system and nothing moves, right? This is consensus. All people have the same opinion, say. Well, so for this kind of system that is very well known and that is paradigmatic, actually for many studies, we say that the system is symmetric whenever the coefficients sigma are symmetric. That is, sigma ij is equal to sigma ji for all I and j. And otherwise, we will say that the system is non-symmetric. Right. So let me recall. You can see here that I have put a number of names. That the Exelman-Krause model is a basic model for collective dynamics or social dynamics, but there are many other models, like, for instance, the very celebrated model by Cocker and Smale and many other variants. Here, I have written quite many names, but actually, I am very far from being exhaustive because in the latter years, there have been many works about collective dynamics. And so I cannot cite anybody, I'm sorry for that. Let me write the Exelman-Krause system in the matrix form. So let us introduce Y, which is the state of the system in dimension capital N, right? Let me denote by capital A the matrix of the system. And then the system above can be written in the form Y dot equal A Y, where finally, as you can see, A is an arbitrary matrix, a square matrix of size capital N, whose coefficients of diagonal, the sigma ij for I different from j, are coefficients that are non-negative, arbitrary coefficients that are non-negative. These are the interaction coefficients. And along the diagonal, as you can see, you choose the diagonal so that the sum of coefficients over every row of the matrix is equal to 0. This is exactly what corresponds to the Exelman-Krause system. Okay, so we are interested in such systems with such classes of matrices A. Okay, another a basic remark is that, well, and let me assume in what follow that for every agent I, there exists at least another agent J, such that the agent I has an interaction, a non-trivial interaction with the agent J. Okay, there is no isolated agent. This is the assumption. Then as a very basic remark, let us denote by E in what follows, the vector consisting of all components equal to 1. Then obviously, because the sum of all coefficients along each row of the matrix is equal to 0, you can notice that you always have A times E, which is equal to 0. That is, the kernel of the matrix A contains at least the line generated by E. But actually, it is a very simple exercise that under this assumption of interaction, and because of playing with, the Gershgorin circle theorem, you can notice very easily that all eigenvalues of A, except of course 0, which is an eigenvalue of A, but all other eigenvalues of A have a negative real part. So what I mean is that except the kernel of A, which is of dimension 1, and which is carried by the direction E, which is all components equal to 1, except of that, the matrix A is Hurwitz. All eigenvalues have a negative real part. Right. So this is a basic remark. Now, how do we do usually in order to prove in two lines that in the symmetric case, we indeed have exponential to consensus, exponential convergence to consensus, whatever the initial data may be? It is very simple. It is very simple. You just observe first that if you denote, let us say, by y bar e as the average of y of t, so this is the scalar product of y of t with e times e, okay, this is the average, then you easily observe by a direct computation that this quantity is constant in time. This is just because you differentiate with respect to time, and using the fact that A is symmetric, you immediately obtain that it is equal to 0 because AE is equal to 0. So this is the first observation. The average of the agents remains constant with respect to time. So then, as you know, in statistics, you know, there are two fundamental quantities, the average, which is the first, and then the second one, which is the variance. So let us look at the variance. And if you look at the variance, and if you differentiate the variance with respect to time, then you observe, because of my previous observation, that the decrease of the variance is always negative. That is, the variance is decreasing. Whatever you do, the variance is decreasing. And then, of course, you obtain very easily, here we are in finite dimension, that y of t converges exponentially to its average, y bar e. We have exponential convergence to consensus. So it is completely obvious, but it is the main argument in order to prove convergence to consensus. In the symmetric case, it is very simple. And we have a statistic interpretation in terms of the variance, and that's great. However, in the non-symmetric case, this very, very simple argument cannot work. It cannot work because the quantity AZ scalar Z may be positive for some Z, right? So you do not have the decrease of the variance. And because of that, actually in the literature, when trying to prove the convergence to consensus for non-symmetric systems, well, the existing methods are actually more complicated. Actually, in the existing literature, there is no, I will put it in quote, there is no L2 theory. What I mean here is that there is no appropriate variance in the non-symmetric case that would be always decreasing to 0. So this is why, for instance, researchers like Jabin, Moch, Tadmor, in several papers have developed what can be called the L-infinite theory, which is more complicated to deal with. As I will come back on this point. So one of our objectives in this talk is precisely to try to develop a L2 theory. That is by designing an appropriate variance in order to prove convergence to consensus in the non-symmetric case. Okay. Our study is also valid in the infinite dimensional setting. That is, when you let the number of agents, capital N, tend to the infinity, then the natural limit that you obtain from the previous finite dimensional system is the following equation, which is now the fact that our state is a function y of t and x, depending both on time and of a space variable x, which is evolving according to that equation here. Dy over dt is equal to an integral over a domain, capital omega of d, of some kernel, sigma, okay? Sigma is the interaction kernel, times y for an agent x star, minus y for the agent number x, okay? So of course, defining the operator A that is written here, you have exactly the same differential equation as before, except that now we are in the infinite dimensional setting. Y dot is equal to AY, where A is that operator. You can notice by the way that A is a kind of Fredholm operator. A can be written as K minus MS, where K is a kernel operator. It's a Hilbert-Schmidt compact operator, and MS is the operation of multiplying by the function capital S. Exactly. And here now in the infinite dimensional setting, the vector E, whose all components are equal to 1, becomes the constant function equal to 1 over the set capital omega. We can note that we still do have AE is equal to 0. I mean, in the kernel of the operator E, you have at least the line generated by E. And also in the infinite dimensional setting, our objective is to be able to understand the asymptotic behavior of y of t, and so to prove exponential convergence to consensus. This is our objective. In order to come to that objective, I need to recall a notion that is well known in the community of Automatica, which is the strong connectivity of a graph. So let me briefly recall it. First, in finite dimension, and then a possible extension to infinite dimension. Let me recall that in finite dimension, when you consider the matrix sigma of interactions, so the matrix sigma whose coefficients are the sigma ij, you can associate to this matrix sigma a directed graph, capital G, and you say that this directed graph, capital G, has an edge from I to J whenever the corresponding coefficient, sigma ij, is positive. That is, when the agent number I has an interaction, a non-trivial interaction with the agent number J. Okay, so it means that when a coefficient, when an entry of the matrix EA is equal to 0, it means that there is no direct interaction between the agents number I and J. And when an entry of A is positive, they are directly connected. And we say that the corresponding graph, the directed graph, is strongly connected if given any two agents, I and J, different agents, there exists a path of agents joining the agent number I to the agent number J. That is, if sigma ij is positive directly, then it means that the agent I is directly connected with the agent number J. But it's not necessarily the case. The coefficient sigma ij could be equal to 0, meaning that there is no direct interaction. But maybe there is another path with a third agent K. And you have first to go from I to K and then from K to J in order to have a path. And there is a path of agents, there is a path of interaction connecting the agent I to the agent J. So this is the notion for a graph of being strongly connected. And you have here on the picture an example where the graph is not strongly connected. Look at, for instance, the agent number 2, which is not connected conversely to any other agent. In that case, for instance, we have 3 strongly connected components. However, if we change a bit the matrix sigma like that, we create 2 other interactions, then I do claim that this graph is strongly connected in the above sense. Okay, this is a classical notion. And this is a notion, by the way, to be compared in some sense to a kind of geometric control condition, but at the discrete level. It's different because there is no propagation like in a wave equation, but you can think of it as a kind of geometric control condition. Now let me generalize, and I'm not sure it is known in the existing literature. Let me generalize this notion to infinite dimension. In the infinite dimensional setting, we now deal with the function sigma, which is the function of interactions, a function of two variables, okay, in some domain capital omega. So in order to give a sense to pointwise values of sigma, we use the concept of Lebesgue points, okay, but there is no problem with that because almost all points are Lebesgue points. And now, given two such Lebesgue points, well, we will say that two such Lebesgue points are connected whenever you can find a path of such Lebesgue points, such that as you can see, iteratively you have this property for the next point of being in the essential support of sigma seen from the latter point. Okay, this is exactly the notion that generalizes the corresponding notion here in the finite dimensional setting. Okay, this is passing to the limit in some sense, thanks to Lebesgue points. Right. So this is the notion that we will use for a graph in the infinite dimensional setting to be strongly connected. Now, given those definitions, and maybe the definition in the infinite dimensional setting is not easily seen from a picture. I'm sorry for that, but at least in the finite dimensional setting, it's easy to see. Thanks to those definitions, we have the following result that we have proved recently with Laurent Boudin and Francesco Salvarani. So we do assume that the graph associated to sigma is strongly connected. And that's the only assumption. Now we can be either in finite or in infinite dimension. What we do claim is that first, there exists a unique V, which is in the kernel of A star. A star is the transpose of A in finite dimension, such that all components of V, or if we are in infinite dimension, the function V is positive. And the scalar product of V with E is equal to 1. This is a normalization condition, that's all. And then you look at the weighted mean of the state y of t, which is that guy, okay? So we look at the scalar product of y of t with V against the vector E, okay? We call it y bar V. Then we do claim that this weighted mean, this is a weighted mean with weight V, is constant with respect to time. And this guy is exactly the consensus limit of any solution of the system. Actually, any solution of the system y dot is equal to ay does converge exponentially quickly to the weighted mean y bar V. This is what claims this inequality. And moreover, we can say something on the sharp exponential decay rate. Well, this is not a surprise. In finite dimension, the sharp exponential decay rate is nothing else but it is given by the second eigenvalue of the matrix A, because the first eigenvalue is equal to 0, right? So of course, it is already, this result is already known in the symmetric case. You can look, for instance, at the famous paper by Olfati, Saber, and Murray in 2004. It is exactly written, but in the symmetric case. You can see also a recent paper by Weber, Tyson, and Much in 2019. In the infinite dimension, we also have an expression for the sharp exponential rate, which is new, which is given by a spectral bound of some operator. And this operator, denoted here by A2, is actually the restriction of the operator A to the image of A. Well, it comes from the proof. What I would like also to say with respect to this main result is that when there is no strong connectivity assumption, then actually we have as well an exponential convergence result. But we have exponential convergence to some clusters. And the clusters, it's also no surprise, are exactly defined by the strongly connected component of sigma, right? What I mean is that in every region where all the gens are strongly connected together, where they do have interactions, then you have exponential convergence to a cluster. Okay, I will go very quickly on the steps of the proof. So the main step of the proof consists of defining the weight, this weight V, which is the key in this result. So let me very briefly show how to define the weight. So first we have to compute the adjoint A star. Okay, so here on this slide is the expression of A star. Okay, you can believe me. Now, for A star, actually, what we do prove is that thanks to the strong connectivity assumption, we prove that actually the kernel of A star is one-dimensional. Okay, and since it is one-dimensional, it means that there is a unique V in the kernel of A star such that V scalar E is equal to 1. Okay, and now the main point and the key point of the proof is actually to prove that this unique V in the kernel of A star is actually positive, meaning that in finite dimension, all its components are positive. This is not obvious. This is not obvious. So once you know that V is positive, you can interpret it as a weight, and this is the key. And in order to prove that it is positive, actually, we have elaborated an homotopy argument consisting to deform the system to a symmetric system. For a symmetric system, a very simple computation shows that the good weight is the function E, whose all components are equal to 1. And then you come back along the homotopy, and thanks to analyticity argument, actually, and thanks to strong connectivity again, you are able to prove that the positivity property is preserved along the path. This is the key point. So once you know that this V is positive, it is a weight, and you can indeed define an appropriate weighted structure, either in a finite dimension or in infinite dimension. You can weight the usual structure thanks to this weight V. You can define here at the bottom of my slide the concept of weighted mean, which gives you exactly the limit of the consensus. And so I will pass maybe about that, but then you have to play, let's say, with the spectral properties of the operator A in order to establish exponential to convergence to consensus. But let me insist that in this proof, the key point is to be able to identify this weight V, and thus to identify an appropriate weighted structure. As further comments, because I have to be quicker, as further comments, let me mention that our result can be as well settled for discrete time systems. There is absolutely no difference. So in the discrete time setting, you have as well exactly the main result. We are able to provide a kinetic interpretation of the system. I do not know if it is useful or not, but we have it. I don't know. Actually, we do not know if this kinetic interpretation may be useful or not, but we have it. Okay, so let me pass about that. And maybe more useful is, again, let me come back to this weight V, because thanks to this weight V, we are now in a position to define the notion of a weighted expectation and a weighted variance. We just take the usual expectation or the usual variance, and we put inside the weight V that we have identified. Okay? Un peu plus tard, s'il vous plaît. Je suis désolé. I'm in my office, so sorry. So we can define in particular this concept of weighted variance. And what we do observe is that if we can use this weighted variance along a solution of y dot equal to ay, and we do observe that if we take it as a kind of Lyapunov function, what we have is that v dot is always negative. It's always negative. And thanks to that observation, our claim is that we have obtained a kind of L2 theory, but this time which is valid in the non-symmetric case. What I claim here is that thanks to this weighted variance, we have found a Lyapunov function, which is a weighted variance, which permits to prove exponential convergence to the consensus, thanks to LaSalle invariance arguments. Actually, what we do hope is that this weighted variance may be useful in some control problems, or maybe in order to prove robustness of that convergence with respect to noise or with respect to some nonlinearities that you can plug into the system. And an example, a first example of how this variance may be used in control problems, which is currently an ongoing work with Laurent Boudin and Francesco Salvarani, is, you know, it will become fashion again in France next year. It's to control the vote opinions. So we have here at the top of my slide, we have a model that is a model of votes, actually. So yi of t is the opinion of the agent number I at time t. So the first term here, you recognize it. It is the term that we have used throughout. It is the Exelman and Krauss term. It stands for the binary interactions between the agents. Okay, the agents communicate together. They exchange their opinions. Here you have a memory term, which is a self-thinking term. And here you put the control. And the control, for instance, can be the influence of media, or maybe the influence of Facebook, or Meta. Sorry, it is not Facebook now, it is Meta. Okay, so it is, in any case, it is the control. And thanks to this control, thanks to this influence, you would like that at the end of some process, all agents think in the same way. So you would like to reach a consensus. And for instance, thanks to the weighted variance I showed you before, we have been able to establish a theorem showing that if, so under a threshold condition, which says that self-thinking should not be so strong, which is not surprising, then we are always able to control all opinions of people. We can control them exponentially, asymptotically to a consensus, thanks to an explicit feedback control. And so I have to end because I'm running out of time. So to end my talk, I would like to wish a very happy birthday to Enrique, who will for sure recognize the different places that are printed here on my slides. Happy birthday, Enrique.
Thank you. Thank you very much, Manuel, for this very interesting talk. I don't know if there is some question or comments.
Yeah, I have a question. So actually, the picture on the left with Malika. So this is in Jean-Michel's birthday, I think, right?
You have a so good memory. Yeah.
Yeah, and the one to the right, I think it was a workshop in Graz. Was it in Graz with Kunish?
Exactly.
Yeah. And then these are Yannick and Guillaume, right?
Exactly. Yes.
Where is Guillaume now? Guillaume Olive?
He is still in Poland, in
Okay.
Cracovia. In Cracovia.
And the one to the right down, I don't know. I mean, this could be any place, but yeah.
Yeah, this is because I cut the picture. So it is
so
also.
This is IHP or?
IHP, yes.
Yeah,
exactly.
it looks like IHP. Yeah, it looks like IHP.
Amphitheatre Hermite. It is also at Jean-Michel's birthday.
Oh, I see. This was on Jean-Michel's birthday. So thank you.
Yeah.
Okay.
Yeah.
And yeah, so great. Are these, you mentioned Lyapunov functions. Is there some kind of Lyapunov equation that characterizes the stability properties you have presented?
Yes, and this is one way of proving the exponential convergence. You are right. We can write an explicit Lyapunov equation for the weighted variance. That's perfectly correct. Yes.
I see.
Yes. The main novelty here in the talk is to be able to treat non-symmetric systems by means of classical Lyapunov function. The price was to introduce an appropriate weight in order to deform the usual structure.
Yeah, but this is why I was asking, right? Because, well, I don't know these things very well, but precisely the Lyapunov equation is meant to provide you the scalar product in which you see the dissipativity of the system, right? Even when things are not symmetric, right?
Absolutely.
Yeah.
So this echoes what I said here at the beginning of my talk. In the symmetric situation, for instance, you take the very usual variance, and the scalar product is the usual scalar product, Euclidean one, is exactly the appropriate one to prove the decrease of the variance. While as soon as A is non-symmetric, well, it is not the case because because the level sets of AZ scalar Z are not exactly circles, but they are ellipses. So you have to deform the space using an appropriate weight.
Right. So this in the limit of I think there is people, maybe Gunther here have I don't remember, maybe, right? So when you make the network denser and denser, then eventually in some regime at least, this could lead to what? Some kind of transport diffusion problem, or I mean, because A would be symmetric, this will be like a.
You mean the kinetic limit? Or am I?
Well, it could be. Yeah, you see, there are several ways, right? So one is looking to agents. The other one is more like the finite difference one, right?
Yes.
I mean, if you just think on these discrete systems, you are considering as finite difference discretizations of a PDE.
I see.
Then there is a regime in which this will lead to some kind of, well, maybe non-local. I mean, there is people here like Mahamadi and so on that are experts on this. This will lead to some, okay, this is the kind of continuous non-local model, right?
Yes, I can answer you in one word, because you know very well that concept. It is exactly the graph limit of
the graph limit, right?
Yeah. Exactly what you did recently with Bicari and Low in one of your papers.
So, but then your sigma here is non-symmetric, right?
Exactly. Yes.
Yeah. Right. And see, so this is more like diffusion plus some drift or something like this, right? Yeah. Okay.
Yeah. Exactly.
Okay.
Exactly.
Yeah. That's very interesting.
Okay.
Thank you.
Thank you. There is another questions. Maybe Fatia Alabo.
Yes, I have a question. Hi everybody. I just have a question for the very beginning. And thank you for the very nice talk, very interesting. Does it make sense to have does there exist models with more than interaction between two agents, maybe with a subgroup of agents, meaning that, for instance, for vote models, as you ended up, you could say that people are influenced by a group of people or something like that?
Yes, absolutely, Fatia. We studied the simplest possible model, right? But there are plenty of variants in which, for instance, you can introduce a certain number of leaders, for instance, a certain number of subgroups in which you have such or such specific influence. There are an infinite number of variants probably that are very interesting to study. Here we studied the very simplest case.
Yeah, but it's very nice. I mean, with this non-symmetric argument and the weight, which has a sign, and this is really nice. Thank you.
Thank you, Fatia.
Okay, thank you. There is another question, maybe Jean-Michel Coron?
Yes, very nice talk. Thank you very much, Emmanuel. I was wondering, with the Lyapunov approach, so you get some exponential decay rate. Is it the same that you observe numerically, or is it conservative?
Yeah. That's a very good question. It's the decay rate actually that we obtain with this weighted variance is not the sharp one.
Okay.
It's not. It's not, because in order to get the sharp one, well, it's more complicated. But at least it's easy to explain in a finite dimension. In finite dimension, what I said is that the matrix A has 0 as a simple eigenvalue, and actually the rest, the matrix can always be splitted, like I'm showing with my mouse here, and the remaining matrix here, A2, is Hurwitz. So you immediately get the sharp decay rate. But in infinite dimension, it's another story. It's more difficult, technically more difficult, because the spectrum of A can involve both discrete and also essential spectrum. And as usual, it's because of essential spectrum that you can lose the property that the Lyapunov variance, the weighted variance I showed you, does not give exactly the sharp decay rate.
Okay.
There is a complication exactly because of that point.
Okay, thank you very much. Thank you.
Thank you. Mahamadi has a question.
Yeah, thank you, Emmanuel, for the nice talk. I have two small questions. The first one, you didn't give the regularity of the weighted function. It's only a non-negative measurable function. You have another regularity, a precise regularity for V.
So for sigma, you mean? Sorry?
No, the V, the weighted function V.
Oh, the V.
Yes.
Okay. No, V is an L-infinite function. That's all.
It's bounded.
Yes, it's bounded. Yes, absolutely. Absolutely. It's an L-infinite function that is also bound, that we show it is bounded below 2.
Ah.
And that's all. That's all we can have, by the way. Because in general, because we do not make any specific assumption on the weights themselves, on sigma. But probably
there is, because the weight you suppose that is bounded is L infinity of omega squared. And that makes difficult to apply to singular integral operator, like Enrique was saying, for well, what happens if the sigma is in L1 log? So,
yeah, I agree with you. I agree with you. What we do not know, it's a very good question that I don't have the answer. If we assume that sigma is a bit regular, then can we claim that V is regular as well? I do not know. I do not know. I will think about this question.
Okay.
It's important. It's important. You're right. You're right.
Thank you.
Yeah, I had also a question about the weight. Maybe you already said that. So did you prove that B is bounded by below and above? So at the end, it is the weight is equivalent to the original one, the norm that defines the weight.
So in a finite dimension, of course, you obtain equivalent norms, this for sure, but not in infinite dimension. Not in infinite dimension. You obtain norms that are not equivalent to the usual ones. No, indeed.
Even if your weight is bounded by below and above.
Let me, maybe I'm telling a mistake. Francesco, you can help me if you have the answer. I'm not sure. So I'm not sure. I'm not sure. So I don't want to make a mistake.
Okay, no, interesting.
I'm not sure. I will think.
Okay, well, thank you, Emmanuel. And I don't know if there is another question or comment.
May I want a question? It's Milton from Peru. Professor Emmanuel, about this model, and we can extend to hypergraph.
Yes.
Model have studied to hypergraph, or still?
I'm sorry, I didn't understand your question, Milton.
Okay. Otherwise, question about the model, and we can extend to hypergraph because you have studied to graph. Okay, when strongly connected. Okay, and I would like to know about the extended to the hypergraph.
I absolutely don't know.
Okay.
No. Yeah,
maybe an open problem.
Maybe, it's maybe another problem with another interpretation. Yeah, that's a very fine issue. I do not know. I absolutely do not know.
Okay. Thank you, Professor. Thank you very much.
Okay, thank you. If there is no more questions, we thank Emmanuel for this very nice talk, very interesting.
It was a pleasure.
Okay, so we have some minutes.
Merci Emmanuel aussi pour autant d'années d'amitié et de soutien et de collaboration. Ça a été sans doute une des meilleures découvertes, ça a été de te rencontrer.
Le plaisir est partagé, Enrique. J'espère que ça durera encore longtemps.
So we are waiting you in Steinbach Brewery, right? For the degustation of the next few beers. Yeah.
When you want, with Günther.
Okay, we have some minutes. Thank you, Emmanuel. We can pass to the next speaker. Are you ready? The next speaker is Fatia Labo. Are you ready, Fatia? Maybe you can share your screen. Okay. Maybe she's not ready. We are 4 minutes ahead of time, so we are okay. No? Technically we are in the coffee break.
Yeah, it's working. And then do you see it?
Yes, we see your screen, but we see all your screen, also the. Now it's okay. Now it's okay. Now it's okay.
Normally,
okay. It's perfect.
Normally it should be okay.
It is okay. It's perfect.
Okay, no, I should not do that. Okay. Yeah. Is it fine?
Yeah. It's very fine.
Apparently there was some delay. I suspect there was some delay because there was a test and normally I knew how to do. I just forgot to open the video and the microphone.
Yeah, but now it's okay. Okay, now it's 18. Are you ready? We can start?
Yeah.
Okay, so
hi.
We pass to the next speaker. For me, it's a pleasure to present Fatia Labo. She was professor at the University of Bordeaux, and then she became full professor at Université Louis Pasteur, and then in Université de Lorraine, no? She will talk about some recent issues on the scalar input bilinear contours of PDEs. So Fatia, thank you.
Thank you for the introduction, and thanks to the organizer for this very nice conference, and happy birthday to Enrique, but I will come back to this at the end. Okay, so even if there is a menu, I will skip some things if it's too long. I'm watching the phone. So I'm going to speak about just the introduction of the subject and some motivation and example, then some very well-known results on obstruction to exact controllability for this type of bilinear control. And then the result we got in collaboration with Pier Marco Canassa and Cristina Urbani, our PhD student, stabilization to the ground state solution for parabolic abstract equation, and some local and semi-global exact controllability result also. And another subject that I developed with Cristina, which is also a constructive characterization of real valued potential functions, which appear in the bilinear formulation by scalar input. Some very short perspective and open question, and some thanks and happy birthday to Enrique. Okay, so I come more from the linear additive control question. And so let me recall that in this case, you have an abstract equation, which the dynamic part, which is this one with A, which generates a C0 semigroup on Hilbert space, in general a Hilbert space, but it can be a Banach space. And then you have the control here, which is P, and B, which is the control operator, okay? And of course, it's subjected to an initial condition. And the B can be bounded or unbounded. And as Marius said earlier, that in general, it means that you have a locally distributed control or a boundary control, or you may have a pointwise control, but in the unbounded case also. So in this model, the control appears as a linear source term. And the aim, if it's possible to control the system, it's to drive the system from a given state to a given desired target, which can be either a final given state, or a given trajectory, and at a prescribed time, or asymptotically. Okay. Of course, the control is going to depend on the initial state and the target. You know. When you deal with a scalar input bilinear control, you start with nonlinearity because you still have your dynamic model. And now the control takes the form, it's a coefficient which depends only on time, it's a real valued, and it acts on B is a control, but is a control operator, but you have the solution which appear also. Okay, so the abstract framework is going to be the same, at least from this slide. And the control P now is a real valued function. And it's a factor, a multiplicative factor of the control action on the state. So in the linear additive control, you have, of course, using the Duhamel formula, this expression for the solution, and you see that P appear in an affine linear but affine way with respect to the unknown which are formed by the U, the solution, and the control. Whereas in the scalar input bilinear control, of course, it becomes nonlinear action. You have a bilinear action with respect to the couple UP. So it changes things. Okay, so typical example, which are well known and well studied, is the Schrödinger equation, where you add a boundary and initial condition. Here, psi models the wave function of the particle. P is the amplitude of the electric field, and it's a real valued function depending only on time. And the electric field is a way by which you control your model. Okay. Mu is a so-called dipolar moment of the particle. It's also real valued, and it's only depending on x. Okay. So the control, as I said, is realized through the intensity of the electric field, and it fits into this scalar input bilinear control model. You have also, for instance, the Fokker-Planck equation in 1D, which looks like this equation. So it looks like a heat equation here, and then you have this B. B is a operator which at U makes correspond mu U derived with respect to x. Okay, so it's unbounded. And here U is with some typo, the probability density of a 1D diffusion process of the velocity of a particle under the action of drag and random forces. Okay. Here the drift, it's a simplified model, and the drift is chosen in separate variable of the form P, which is unknown, and mu. Okay. And once again, P depends only on time, and mu is a given function. Okay. But you have other physical, mechanical, or chemical models of bilinear control. You have heat-based model, such as appear in nuclear chain reaction, modeling production of neutrons in fission. I mean, but of course it's simple models. You have mechanical systems such as beams, modeling smart materials. Okay. So to summarize, we have a physical system which is approximated from the modeling point of view by a dynamical system evolving through time and space. And we want to act on this system, once again, to drive from one state to a target one. These questions are common for linear as well for bilinear control. But as I tried to show through these few examples, is that for certain physical systems, the control affects directly the state as a coefficient. And so you have a nonlinear action in a bilinear way, and it changes. I mean, the fact of controlling changes this dynamic. You switch to bilinear control. Okay. So also let me point out that one should distinguish scalar input bilinear control from multiplicative control, because in multiplicative control you have the control is depending on time. It's nonlinear, but it's depending on both time, and it takes value in the infinite dimensional vector control space. Okay, state space actually. Okay, in scalar input, as I said, it depends only on time. So in the second case, you have, of course, much more degrees of adjustment or of control. And this explains, at least in some ways, the first pioneering results which were obtained, which were negative results. And there is so now I will speak shortly about obstruction to exact controllability for such scalar input bilinear control models. So I go back to this bilinear control with scalar input P, with the framework that A generates a C0 semigroup of bounded linear operator in a Banach space of infinite dimension, and B is a linear bounded operator on this space X. So we get back to the set of states which are accessible from any initial condition, which is, I think I switched the order and I I forgot to transfer. So let me denote by U of the variable t at corresponding to the control P and the initial data U0 of this problem. One can show it's well posed in suitable spaces. you define the set of states which is accessible from U0 by this definition. S of U0 is all the trajectory that you can reach with any control in which is in LR locally, 0 infinity, with values in R. And R can be any real above strictly from 1, okay, and finite. Then there is a very well-known famous result by Ball, Marsden, and Slemrod, which go back to the early 80s of the last century. Assume the above hypotheses on A and B. Then for any initial data in our infinite dimensional Banach space, this set of accessible, reachable states is contained in a countable union of compact subset of X. So in particular, X minus a complementary of S of U0 is dense in X. So it means that your set of reachable is very, very meager. I'm not sure of my English here. Okay. And in this seminal paper, they gave examples to beam and wave equation, and in particular in link with the non-harmonic Fourier series. Later on, there were negative results which were also proved for quantum control system by Turinici in the 2000. And I discovered recently Enrique, a very nice article by Enrique, which remarks on the controllability of the Schrödinger equation, not only for bilinear control, scalar input bilinear control, but also for nonlinear control and a question about numerics. And there is a very nice presentation on of the reason for obstructions, also links with the additive control question and the Hilbert uniqueness method, and also challenging question for these bilinear control issues when you have a scalar input only. Okay. Since then, I'm not an expert, so sorry if I forgot some people. I just write a very short list. There were previous work by Karin Bochard using Nash-Moser because there were laws of derivatives based on inverse function theorem, but with a loss of derivatives. And a very nice result with Jean-Michel. And Jean-Michel also with negative results and also the existence of minimal time. And there was a result by Bochard and Laurent, and Bochard alone, which facilitates the result because there was a hidden regularity property, and they could simplify and find the right spaces in which to set up the problem to have positive controllability result, and also for nonlinear Schrödinger equation. And there are also very nice results by Bochard and Morancet and Bochard and Marbach, more recent. Okay. So as I said, it has been widely studied by different methods, so I'm not at all going to be exhaustive. But for multiplicative bilinear control, so that's different issues, and with application to reaction diffusion equation, you have works by Canarsa, Floridia, Kapalov on the reference therein. And for result based on Lie brackets and Galerkin approximation adiabatic methods, I refer to works by Bosquin, Sigalotti, and the group. And let me go back to the subject of this talk. And as I said, Enrique's article, which explain why and which type of properties the potential, the mu, if you think to Schrödinger equation, the mu, which appear, you have the control, the bilinear control, which is the term P of t, which is your control, time B u, and B in general, not always, but is a multiplication by mu, by the function mu, which is real, okay? And you have to ask several properties on this function mu. And to get a chance to reach larger and identifiable sets for which you have controllability that you can reach. Okay. So I will not detail a lot, but if you denote by lambda k phi k the eigenvalues and the associated eigenfunction norm to 1 for the operator A. Okay. The link between the uniqueness property when you think to approximate controllability for the linearized control problem associated to your bilinear problem, then you realize that you need this type of non-vanishing condition, and it's very well explained in Enrique's article. But you can find it also naturally by decomposing your solution on the basis, the orthonormal basis formed by the eigenvectors of A. Okay. In general, if you want explicit results, you need also gap conditions and asymptotic behavior. This is, for instance, the case in Beauchard and Laurent paper. So this gives a frame in which we work, but we were interested on E-type equations. So our abstract model refers to a parabolic equation. And for the second part of the talk, I will answer another question, which is related to what you can hope to say about mu. Can you find practical ways to exhibit large classes of function mu that satisfy this non-vanishing condition, asymptotic condition for these scalar products? Okay, so let me start with our first result, which is stabilization to actually local super exponential stabilization to the ground state solution for parabolic abstract equation. So our model is this one. Here we assume that X is a separable Hilbert space, B is a bounded operator on X. The control evolves in N1 lock. We will work with L2. A is a densely defined linear operator, which is self-adjoint, which satisfies this. So you admit negative eigenvalues. For instance, we assume that there exists a lambda strictly bigger than this, that you have some compactness property. Okay. And under this hypothesis, we denote by phi k the eigenvector which form an orthonormal basis. We denote by lambda k the eigenvalues. They can be negative. Sorry, I forgot to correct this. They can be negative for some of them. For this part, I will specify when we will assume that sigma is 0. And minus A generates a semigroup, C0 semigroup of contraction. Okay. So using standard result, I will not develop here, but there is well-posedness in the space of continuous function on zerity with values in X. And if the solution is more regular as long as soon as you go away from 0. Okay, and also if the initial data is 0. Okay, what is called the ground state associated to our control system is just the solution of our bilinear control model when P is set up to 0 and you take as an initial value phi1. That means the first eigenvector associated to minus A. Okay. More generally, we denote by psi g the eigensolution of A, defined as the trajectory corresponding actually. Okay. Again, when you set P, the control is equal to 0. A short remark, trivial. If A is assumed to be coercive, that is, if lambda 1 is strictly positive, then of course the solution of our bilinear control problem trivially is exponentially stabilizable to the ground state. This is trivial. So Okay. So let me introduce some notation and introduce the following definition. We say that 2 is locally exponentially stabilizable if we have this kind of property, and as I showed before, if lambda 1 is strictly positive, you have trivially this property. Okay. Now we say that it's locally super exponentially stabilizable to a given trajectory you issued from a control P bar in L2 lock and use an initial data U0 bar. If we locally, for any row, strictly positive, and for all initial data close to U0 bar, we can find a L2 lock control such that the trajectory corresponding to U0P is close super exponentially to your reference target. Okay. And let me also make the following remark before giving the first result and some sketch of the proof. Okay, so if lambda g for a given g is 0, then phi g, the eigenvector, as a solution, phi g as initial data and 0 as control, solves our bilinear control system. And under the assumption that lambda g is equal to 0, the linearized system for our bilinear control around this reference is exactly this equation. Okay, we will have assumption on this equation, so on the linearized model, and this is rather common. So our first result concerns local super exponential stabilizability for 2 under an exact controllability assumption for this linearized system. And in the first part of the proof, for which we assume that lambda g is equal to 0. And there is a simple argument to deal with the case lambda g is not 0. So we do not prove that only for the ground state, which is the case g equal 1. You can do it for any j. And the more technical part is, of course, the first part when lambda g is assumed to be 0. Okay. So we introduce the following natural condition. Let t strictly positive be a given time and AB satisfying the assumption we gave before. We say that the pair AB is G null controllable in time t if there exists a constant which may depend on t, in general yes, such that for any initial data y0 in x, there is a control P in L2 which satisfies this cost estimate, and such that the solution of your linearized equation is vanishing at time t. Okay. A corollary definition is that it's said to be G null controllable if there exists a time for which it's true. Okay. Let me remark that the control cost is given by this relation, if it exists. Of course, it can be infinity. We are not interested by this case, but okay. So our first result, which is we assume the above hypothesis, and we add the fact that the pair AB is assumed to be G null controllable. Then 2 is locally super exponentially stabilizable to psi g for any g bigger than 1. The difficulty is to have condition which guarantees that AB is G null controllable. Then you have to use the moment method and to have an precise estimate on the cost function for the linearized problem. So here we add the following assumption. We make the assumption we did before on A, but we assume now that we have the following gap condition, which is satisfied. And on B, we have, not very surprising, the type of non-vanishing condition we saw before. Think if B is the multiplication by mu, and the scalar product is just the L2 product, you go back to the integral over omega of mu psi g psi k is non-vanishing for all k larger than 1. And we ask for more than an asymptotic behavior. We ask that this series is finite. There exists a tau strictly positive that we have, this is finite. And there are several examples in 1D or in radial case. So when you use the moment method, unfortunately, you have to switch to 1D result or in a ball with radial arguments. So under this hypothesis on the lambda k and on B, you get that the pair AB is G null controllable. So as a corollary, combining the two results, you deduce that under these conditions, 3, 6, and 7, you have super exponential, local super exponential stabilizability. So as I said before, these vanishing conditions are not surprising. They appear in the Ball, Marsden, Slemrod paper, in Zuazua paper, in Bochard-Laurent, and in many papers. Also in the papers by Bosquin, Sigalotti, and okay. It also can be easily checked that this condition is absolutely necessary for the linear system using Fourier expansion of the solution. So a very simple example of application, the 1D heat equation with Dirichlet boundary condition. And you take the multiplication operator by a sufficiently smooth potential function mu. Actually, the smoothness is that mu is in H3 of 0, 1. Then we know the lambda k and we know the eigenvalues. And the gap condition holds with alpha equal pi. The fact that there is a shift with lambda 1 is a detail. It can be, you can prove it easily. And moreover, one can show that if this quantity are non-vanishing, is non-vanishing, and this infinite set of non-vanishing condition is satisfied, then we have, I go back because I suspect 7 is the condition on B and on this condition. And this comes from, we adapt some arguments from Bochard-Laurent. And an example is that mu of x satisfies this sufficient condition. So they also hold for heat equation with Neumann boundary conditions. We gave example with variable coefficient, radial solution of the 3D equation set in a ball. There is extension to degenerate parabolic equation due to Canarsa and Urbani. So let me give a very short, because I'm maybe running out of time. I have to be careful. Oh yeah, so I will switch very quickly. We make just a difference between the solution of our bilinear control, in the case lambda g equals 0, and the solution when p is equal to 0, and you start with a trivial solution pg 0. Okay. Then this solves these nonlinear control problems with non-homogeneous with this term. Okay, and we keep in mind that we have this type of estimate. We can prove that actually that if we consider v minus y, which is correspond to u minus cg minus y. So we want, of course, W to be small. It solves this problem with V as a source term and P. Okay. Then what we can prove, I will not detail this. Okay. Under this type of condition, we have an iterative process argument. We construct intervals of time. Okay. And for which we have initialization process, and then we go back the induction process, And we, using the fact that AB is generally controllable, we drive back y to 0, and then we can end up with this type of estimate. And this is what allows us to conclude. When lambda g is 0, we make this short transform, and it works. The proof of the second theorem involving the gap condition relies, as I said, on the moment method and sharp estimate on B-orthogonal families and control cost due to Canarsa, Martinez, and von Kostenov. We do not use directly the inverse function theorem. We can do it directly with a very nice quadratic estimate on W. The solution of the W is, I recall, U minus CG minus Y. And that's the reason why we can have explicit estimates. These were our first results. Thanks to some discussion with Jean-Michel, we ended up with a more precise theorem, which is exact controllability issues. So we assume the former hypothesis on A and B. Again, that AB is generally controllable in any time. Okay, but now we suppose that the control cost for the linear system satisfy this estimate for small time, for a given time t0, where nu is strictly positive. Then we can prove that for any t, capital T, there exists a control constant RT such that for any U0 in the ball of center psi G and RT of radius RT, there exists L2 control such that you can drive back at time capital T U to psi G. And we also prove explicit estimate on the console cost. Once again, precising assumption on non-vanishing condition and this type of condition, then the pair AB is null controllable, and we can apply what we done before. This can be generalized because we have a parabolic type equation to semi-global result, two semi-global results, this one and this one. So I will skip fast because otherwise I will not end up, especially this one. So in particular, what it means is that we have we can show that every initial data which is not orthogonal to phi1 is controllable to the evolution of the dynamical system without control. It's not exactly, it's controllable to this, the projection on phi1, on psi1, the ground state. And here we assume that A is accretive, so that sigma is 0. Before not, but for these two results, we have to assume that. So I skip this. And the question I was wondering when I started to work on this was this strange condition, very weird for somebody coming from linear control, but you understand that you cannot avoid it, at least from this, it's a necessary condition. And I go back to, again, Enrique's article devoted to the Schrödinger equation, because he defined the elements of the infinite matrix as this one, when you think to be the multiplication by the real function mu. And it's not only that you request that these coefficients are non-vanishing, to have asymptotic properties, like in a Bochard-Laurent paper. What is pointed out in Enrique's paper is they also play a crucial role in the choice of the functional spaces and the norms you have to deal with if you want to get positive controllability results linked to Hilbert uniqueness method associated to the linearized problem. Okay. So when I started to stick to that, I was not satisfied because I say, okay, in practice, one can prove that this non-vanishing condition hold generically, at least in 1D. But in practice, it is hard to exhibit large classes, and when I say large, infinite, classes of function which satisfy this. And also the ability to provide such example rely on the explicit knowledge of the eigenvalues and eigenvectors of A. So what we worked on with Christina was to find an analytical method, and constructive, because in the sense that it leads to algorithm, to build large classes of such potential function. Okay, they can be polynomials, but also other classes of function with different properties than the usual ones which are exhibited. They also satisfy the sufficient condition on B that you require either for our stabilizability result, our controllability result, or controllability result by Bochard, Laurent, and several people. It has a flexibility, and also you need only implicit knowledge. That means we were able to do it with PDEs with more general boundary conditions, so such as mixed, Dirichlet-Robin boundary condition. And it applies to not only heat equation, but dispersive equation, wave equation. And as I said, it leads to an algorithm. So let me just give the application to this model with Schrödinger equation, but here subjected to Dirichlet condition on the x equals 0, and this Robin condition on x equals 1. So this models the motion of a quantum particle in a box with a perfect reflecting wall at x equals 0 and a non-standard wall at x equals 1. And there are references with physicists which studied such models. Okay, so one can prove then the following theorem, that there is an infinite class of mu using our analytical method and algorithm, and such that the lambda, the coefficient Enrique introduced, satisfies this asymptotic behavior, and you have a local exact controllability result with I will not detail, sorry for that, but I'm running out of time. So this extends the Bochard-Laurent result for Schrödinger equation to the case of mixed condition, and here you deal with H2 instead of H3, but this is not surprising. We gave also other application to parabolic equation, wave or beam equation. So this is only the beginning, and there are many things we still don't know. We are working on extension to unbounded operator. It's a work in progress, almost done. Of course, there is something which is not satisfactory. It's that whenever the moment method is used, it reduces the scope. But I have no idea how to do, but that's a very interesting question. And of course, sublinear parabolic dynamical systems and more complex model if you put non-linearities in the B. Numerics. Yeah. And now let me end up with thanks to Enrique. At first for the mathematics you brought in the field of control theory, because when I read your papers, I learn a lot, or when I discuss with you, that's the case for lower energy estimate for other part of my work on hyperbolic equation, and I gain a lot from discussing with you in Bilbao. And we started in 2009, 2010, if I remember well, a very rich partnership with the BECAM, the research center you initiated, and the Centro de Ciencias de Benasque. Giuseppe Butazzo spoke about that this morning, yesterday, sorry. And for the recurrent biannual biannual workshop summer school, created by Enrique with Gunther, and then and with Giuseppe, and Olivier Glass joined later. And this was done, and we had also an important partner with the Center for Modeling in Santiago de Chile, within the GDR on control of PDEs that I directed from France, and the GDR on control of PDEs that I coordinated for France in partnership with Pier Marco for Italy, and with Olivier and I'm sorry, I'm running of time. So we could organize a lot of events, And I thank really Enrique for creating this very rich interaction and mixing young, junior, and senior through conferences, schools, workshops, and collaborative research. So I ended up with this. Happy birthday to you, Enrique. Thanks for all the mathematics, all the dynamic of researches you brought in the field of control of PDEs and in more larger field, and in several institutions and worldwide. Now we are in Erlangen, and I'm happy to be here and to write this, to give a talk, and thank you for that, and for bringing all this to the community.
Thank you. Thank you. Merci, Fatia. Merci. So I really thank your words. Actually, you have been a constant support, not only for me, because you are a supportive person. So I think you have this, not only the mathematical talent, but also this special, say, personal and sensitivity, this social engagement, this spirit of renovation of, community. And yeah, I mean, for me, it was people like you were really those that, made things easier and worth continuing, right? So we know now for each other for many, many years. Yeah. And yeah, I mean, I'm very glad that you are here today with us. And but I wanted also to take the opportunity to thank you, right? Because, you, and without you and many others, we will never have got all these little things you mentioned, that when you pile them together, well, I mean, it's fine, right? Mm-hmm. Thank you.
Thank you. Thank you to you. And thanks to the organizer too. It's really nice to be here, even if it's virtual.
And we wait for you in Erlangen, okay? But be trained on your bike before you come, okay?
In a long time, I didn't bike.
The city bike.
Is it? Yeah, but is it flat? Because I tried to bike in the Pyrenees. It's not enough flat.
No, it's flat for me. I can invite you to Bayreuth. This is not flat, so then you have to exercise.
Then I need to go with Marius and do some training. A lot.
Thank you, Fatia, thank you for the talk. I don't know if there is I think there are some questions. Jean-Michel Coron is raising the hand.
So thank you, Fatia, for this very wonderful talk, and very interesting also. I have a question about P of t. So you have this control P of t. Is it possible, instead of P of t, to use P of u? And u, of course, it's maybe a complicated function, because it's not P of the norm of u. It could be P of something non-local, or some complicated function on u. Is it possible to do something like that?
Right away like that, I don't know. We have to, because we're really using, if it's a P of u, it's not, I mean, we have to do work. I mean, this is not direct, actually. But that's a very interesting question. Okay. No, I was thinking but maybe also thinking to the work by Bochard and Marbach. It found very nice. It's when B is nonlinear with respect to U, also. But I didn't know that there were models where you could have P depending on U.
But this would be the control, so you can do what you want. So you can.
That's a very interesting question. But I don't know. It's not right away, because we are really using the structure.
Okay. Thank you very much. Thank you.
Thank you. I don't know, there is another question or comment? If not, I have a question, Fatia, for the algorithm. You say that you are able to use, even if you have only partial or implicit, I think you say, knowledge about the Eigen function.
Yeah.
So it works in do you have constraints for the dimension? I mean, it works with 2, 3.
No, but no, it works in 1D. Actually, this kind of condition, you have it when it's 1D, and you can say something. Otherwise, but the idea behind is that it's not easy to check at all. Especially if you look at the Robin problem we looked at, the lambda k are not known explicitly. You know the form of the eigenvectors, but not of the lambda k. So the idea behind is to say, okay, you have the lambda k and the phi k, you have this strange condition, which is new for me, totally new. And I say, okay, but behind you know that lambda k, phi k are linked to a spectral problem. And the idea is to use that. But it's very technical. I mean, the architecture of the ideas is, I can explain it, but a lot of computation, a lot of analysis behind, and then there is an algebraic part. But it's rather technical. But the idea behind for me was your lambda k and phi k, they are not hazardous function. They are linked by the spectral problem. So they are linked to A, and of course you should use that. So we found a way how to use that. I mean, you have to trust that there is a magic formula, but I was trusting that there were magic formulas. And we were able to prove that there were a magic formula, but it gives much more information. I didn't have time to detail. It gives much more information. But
okay,
it's 1D. And anyway, when you use a moment method,
of course, yeah, of course.
You end up with my concern is really to say, do we have also some latitude to with another point of view of not only looking for P but looking also for mu? This algorithm it's only partial, but it's a first step to, because the algorithm, as I said, gives more information. You can have something which seems to be not nice, then you can show that you can change this functional space where to set up the problem, and then your mu becomes okay. So, but since it's very intricate, very technical conditions, but the architecture is natural. But at the beginning, you have really to hope that something is going to work.
Okay, I see.
But it's one.
Thank you very much. Yeah. There is another question in the chat. I don't know if Reginaldo can ask directly. If not, he's asking if this result still holds for the degenerate operator.
Which result?
Well, I don't know.
Because there are several ones. I mean, as I said, the part with stabilizability, exact controllability, they hold. The result for generate operator were done by Pierre Marco and Christina. Yeah, it works. No, the stuff is that we were aware that there were results on hyperbolic equation and diffusive equation, and almost nothing on scalar input bilinear control for heat equation. So we started on this basis for Christina's PhD, actually. And we thank also Jean-Michel, who gave indication, and that's we could get the second result. So thanks to Jean-Michel. With more expert than for me, it was new, completely new.
Okay, thank you very much. So we thank again Fatia for this very interesting talk. Thanks
you very much. Thanks to all of you. I love Chile.
Okay, so I think it's time we can pass to the next speaker. So Jaime, are you there? Are you ready?
Yes, here am I.
Okay, can you share your screen?
Try to share the screen. Okay. Can you see my screen?
Ahora sí. Now we see it. Very nice. Okay.
Okay. Well,
we have
first,
a couple of minutes. Are you ready? We can start?
Oh, we can, as you want. Oh, have a couple of minutes if you want. I'm ready anyway.
Okay, there are almost 2 minutes, so I think we can start. So, okay, for me it's a pleasure to present Jaime Ortega from Universidad de Chile. He obtained a PhD in mathematics from Universidad Complutense under the direction of Enrique. now is full professor of Department of Mathematical Engineering and researcher of the CMM in Universidad of Chile. So Jaime will talk about stability estimate for the semi-discrete linearized Benjamin-Bonner-Mahoney equation. So Jaime, thank you.
Okay, thanks a lot for me. Well, firstly, thanks to Carlos, Rodrigo, Sebastian for this hard work. It's this wonderful Congress. For me, it's really a pleasure to talk here. I'm, as I told yesterday, one of the estimados, the old student, Enrique. And it's a pleasure to see the friends, to be part of this party. This is the first thing. Okay, I'm going to present some new results of one of my students. This work in collaboration. This work is in collaboration with Rodrigo Lecaro from Universidad Santa Maria and Ariel Perez, which is a PhD student. He is close to finish his work. First, I'm going to see this picture. We met several years ago in Bilbao for celebrate the anniversary of Carlos. For that reason, firstly, happy birthday, Carlos. It's a real pleasure.
Many thanks, Jaime.
We are here celebrating another anniversary now. It's the contrary. Okay. For that reason, it's a pleasure to be part of these things. Okay. Well, the sketch is, I'm going to talk a few, what are discrete and continuous. This is an old questions and what happened with unique continuation properties and some references and results. And I will not enter to the technical details because are very hard, but I'm going to try to explain something. Okay. I took an old slide of Enrique. I thought from in 2020 and 2012, Enrique in the Congress of Chile put this slide. He say the control problems and now inverse problems are in PD are very important. They are important because they appear in several real applications. It's in quantum mechanics, in optimization, in control, fluids, everywhere appear these kind of problems. And for that reason, it is natural to ask what happens.
Is to make a kind of social.
Sorry. Okay, continue. And it's quite natural to ask what happens when you go to numerics. It is important the numerics for when you are thinking in real problems. For that reason, as Enrique said in that Congress, this need a new analytical tools in anything we're facing numerical simulation problems. And for that reason, it's an old question, but with a natural and easy question with a very difficult answer. Okay. What happens when we are thinking in the continuous problems? The unique continuation properties appear in very natural way. The controllability of PDE are well related with unique continuation property, with Carleman estimates, and so on. More recently, a lot of people which work in control problems begin to start studying inverse problem because they are very, very close in the techniques. The use of Carleman's inequality, the use of unique continuation properties appear also in natural way. When you study the identifiability and stability results, for that reason, it's natural also when you are studying an optimal control problem, what happened with the minimizer problems, what happened with the critical points. For that reason, it's natural. You have a discrete problem. The question is, if the mesh size goes to 0, it is real that the discrete problem converges in some sense to the continuous problem. This is very, very natural question. And the other one is, if I want to study the control, the continuous problem, if I can use some kind of convergence in order to have that the discrete problems in finite difference and finite element method, this converts to the continuous problem. For that reason, these are more or less the questions. As I said, the question is natural. The answer is not natural, as it's difficult. Okay. What happened with the discrete problem? Okay. Firstly, a lot of people which work in control here know that the unique continuation properties are very well connected with the control problem, the so-called quantitative estimates. Okay, what is a classical definition of unique continuation property? We have an equation P de U is equal 0, and U is 0 in a suitable region, could be in the interior, in the boundary, or wherever. The answer is if U, that implies that U is equal 0. Okay, this is the question. But when we go to find difference, a very classical control sample of with due to Odaret Kavian appears in the notes of Enrique also say this is not true. For instance, we can take the discrete Laplacian, the classical discrete Laplacian with 5 points, okay? U is 0 here and U is 0 in these two lines. The only thing that we can see is U is equal 0 in the red points. But we cannot assure that U is 0 in all domains. For that reason, the first question of unique continuation property holds for continuous, but does not hold for the discrete in a classical, in a very simple case. For that reason, the question is what we can do, what we must do to have the results, or what happened in this kind of things. Okay. Well, what happened? Why these problems appear? Well, there is a note of a paper of Enrique in Science Review where he put this example, okay, this classical example of eigenvalues of the spectrum of the Laplacian. And what is the problem? Well, appears some eigenvalues which does not converge to continuous case. Okay, that appear several eigenvalues which are due to the structure of the discrete case, and this make a lot of noise in all those things, and we cannot have the continuous results. Well, for that reason, there are several people who have begun studying this problem. There are several works of Enrique also, but also there is work of Sylvain Hervedosa and Lucy Boudouin, where they study the one case for hyperbolic case. Okay, Frank Boyer and Larousseau have several works also where they want to study what happened with control and try to obtain a Carl-Lemon estimate for several equations, in particular for elliptic case. There is a nice work of Sylvain Hervedosa and Frédéric de Gournay, where they study the Laplacian operator because they are interested to try to obtain a result for the well-known Calderon problem, that the classical inverse problems. And there are another work for the semi-discrete Carl-Lemon estimate for parabolic equation of Boyer and Larousseau. And recently, there is a fully discrete Carl-Lemon estimate for parabolic operator due to Hernandez Santamaria and Gonzalez. But there are several another work, but I not mention all here. Okay. In this work in which we are interested, we want to study the so-called Benjamin-Bonham-Mahoney equation. The classical BBM equation have this structure, and it's a model proposed by Benjamin Bonham-Mahoney in 1972 as a model for the propagation of one-dimensional, unidirectional, small amplitude long waves in nonlinear dispersive media. Okay, this is one of the equations from the family of the dispersive equation. Okay, but this equation has a very particular thing because he has a very particular infinitesimal generator for the semigroup. Okay, which is this one. Okay, here are some references of this problem. Okay, in particular, I mentioned the work of Lionel Rossier and Binyu Zhang. Okay, where they develop a unique continuation property in a periodic domain and uh, and uh, and so on. Well, in a work for Enrique with Xu Zhang, they study a linearized version of EVM, but with a potential ADX which depends on space, which depend on the space. And the question is, what happened with unique continuation property? And they say, well, if we consider suitable boundary conditions, in particular, they consider u is zero in the both stream of the line, and then the solution is the unique solution of this problem is u equals zero. Okay, but with some suitable condition on alpha and beta, which are the potential of the equation. Okay, and Solimbiku also proved another result, consider alpha equal -1 and beta equal 0, and they study also some controllability results. The question is, what happened if we go to the discrete case? Okay. That is the few area. Okay. Why we fall on this problem? Because with Lucia Teresa and Rodrigo Lecaro, we were working. We have a working in progress in which we are interested to study Carleman estimates. Carleman estimate, but for the Calderon problem. That means we want to have some unique continuation property for the Laplacian, but with boundary terms. No, this problem is quite a nightmare. We have a couple of years working on that, and the computations are very hard, but we hope to have results very close. Okay, but this allows us to obtain some results on some discrete Kalman estimate for the Laplace. Okay, but what happened? Well, Yamamoto in a work, he studied the linearized BBM equation, and he proved that if you have a suitable Carleman estimate for the Laplacian, you can go and to obtain a good result, a unique continuation property for BBM equation. Okay. This is a few. In particular, Yamamoto established for this equation where he have a time and space dependent potential, okay, and he showed and he showed that if u and the space derivative are zero in one side and u is zero in the other side, okay, at the initial time, then you have the u is equal 0. Okay, this is, you need to start with this condition. Okay. Well, our idea is if we can repeat the same result of Yamamoto, but when you go to discrete case. Okay. This is a few idea. Okay. Well, the first thing is which is the BBM, the semi-discrete equation. Okay. Well, the first thing is you can discretize. You have a semi-discretization. That means you discretize only the space, not the time, and you can rewrite in finite difference equations the BBM equation and give you this model. Okay, we consider the same finite difference approximation of Enrique. Okay, and when you go to continuous case, okay, you can see that you can have some Carleman estimates for this case. That means if u is small enough regular, for you can have a couple of weights lambda 0. For lambda 0 is sufficiently large, you can prove that exists a constant S0 which depends of these quantities, such that you have this Carleman estimate for is bigger than U0. Okay, and from a corollary of the work of Yamamoto, okay, you can prove that if U is a solution of the linearized BBM equation satisfying these two conditions, then U is equal 0 everywhere. Well, what is the proof of the results in the continuous case? The idea is to try to consider weights of this sort, okay, that you have a double exponential weight, E exponential as phi, where phi is LC. With C must verify the same condition. The condition is we need the sign of this derivative. Okay. With this condition, it is possible to construct a Carleman estimate for this problem. Okay. I will not enter to the computation because it's quite long, and you can have this estimate. Okay, but the idea is if you have this estimate, which is come from the Laplacian, then you can make a change of variable, and then you can obtain an estimate for VBM, for linearized VBM. Well, what you can see in the case of discrete BBM equation? Well, the first big problem when you go from the continuous case to the discrete case, the big problem is you cannot take or the main thing in Carleman estimate is when you have the Carleman estimate, you can take the values of the parameters as large as you want. And in that sense, you can banish several terms on the inequality, and in this way you can get the unique continuation property. Okay. But the problem is when you go from continuous to discrete, the parameters that appear in Carleman estimate cannot be taken arbitrarily and have a strong relation with the mesh, and this is the main difficulty. Okay. Well, which are the things that we have? Okay. Well, the thing that we say is if there exists a size of the mesh A0, which depends on the norm of the potentials, and if you consider these two terms equal 0 for all time, and U equals 0 in an internal mesh, then U is equal 0 everywhere. That means you can repeat in some sense the same result. What are the problems when you begin to start working in these things? Well, you need to define several different mesh which appear, because when you work with when you make the integration by parts in the discrete case, you need to work with the classical mesh, but you need to construct a couple of mesh called the dual mesh, which are not only the points. We need the middle point of the point of the mesh, and you need to consider this boundary, and you need to define also which is the boundary in the cases, and you have several boundaries in the computation. Okay. And also, you need to consider for the integration by parts several operators which are not consider only the points of the mesh, they consider also the middle point of the mesh, and you need to compute some quantities on that. Okay. Also, you need to redefine which are the normals and the trace of an operator. Okay. What we can prove in our case? Okay, the result says, well, if we consider a weight verifying the several condition, the same condition. That means we need a sign of the space derivative for lambda 0, a parameter large enough. There exists another parameter E0 and H0, which depends on the north of the weight, and a constant C, but this constant is independent, such that we can construct this estimate. But we must know that S, the parameter S in the Carlem estimate, cannot be arbitrary. This parameter S has a strong relation with the size of the mesh. And these results is quite similar to the ones obtained by Silvana Redosa and Boyer, but depends on the equation. They have several powers of this one, 2/3 or 1/2 or something like that. Okay. Well, what is the idea? The idea is when we have this equation and we can rewrite this equation in a way as a parabolic equation, okay, with the Laplacian, and we put all terms in the other side, and we will use the Carleman estimate for Laplace. This is the main idea of the proof, okay, and as I told, we need to define several operators. I want to pass, and the good thing is we can try. It is possible to recover several of the estimates at integration by parts that the people use in the discrete case. Okay, for this case we follow all the notations of François, but we can continue with this, and with this discrete Carleman estimate, we can obtain our result. Okay, and but let's and of course we need also a discrete version of the weight inequality. Okay. Well, which open problems here, but this is a starting point of the problem. For that reason, the first thing is what happens when we go to another dimension. If we want to think in problems in 2D or 3D, well, it is not trivial because the way to work with the boundary condition is not easy, and when you go to different directions, to more dimensions, appear several extra terms in this estimate. The second question is we obtain the result for the semi-discretized problem. The question is we can go to a full discretized problem. We think that it is possible. And the other question is this is a linearized case. What happened with the nonlinear terms? And this is something to do, something to think. Maybe the idea will be try to use some fixed point theorem, but we must think a few about that. Okay. Well, happy birthday, Enrique. Thanks for the invitation, and this is your picture in a corner close to the faculty in Gorbea, esquina Chaurren. Thanks a lot.
Thank you, Jaime.
Thanks, Jaime. I don't know if there is some question or comments.
Well, I have a comment, right? So because Gorbea, I mean, this picture is taken near the CMM. We were visiting at that time, Jaime and Rodrigo, together with Carlos and the others, took care of housing us there during the summer 2013, summer in here, winter in Chile. And then walking in the street, I realized that I was living in the corner or very close to the corner between Echaurren and Gorbea, right? So maybe these names don't say anything to you, but when you are Basque born, you immediately identify, right, that these were also Basque people, you know. And then checking, I realized that actually Gorbea was one of the founders of the University of Chile, no? Jaime, I don't remember exactly what the details was. I think Gorbea was born in Vitoria near Bilbao, and then he went to École Polytechnique in France. He was a student there. And then the leaders of Chile came to France to hire the best young engineers, right, to do the civil works of the roads and the highways and the tunnels and the trains to build the infrastructure of Chile. And then Gorbea went there, and other than working as an engineer, he founded the university. Okay, so this corner is there, and I mean it's it's one of the memories we have of this fantastic trip in 2013, where I mean, and this was the Chile plan. So Chile plan is 1 day, 1 kilo, right? So I mean, the food, I mean, everywhere, right? So we were even in the house of Neruda, right? We were having
yes, I
lunch
remember.
in Valparaiso, in these balconies, in the terraces. I remember with Carlos and Lola and Jaime. And okay, so that was a fantastic experience. Yes. Okay. So thank you, Jaime. Jaime is one of the estimados. Estimados is that time where there were, I don't know, like 4 or 5 simultaneous PhD students, and then there was not email essentially, and then we were communicating with documents, and then I would use to write some notes with several problems and make xeroxes and put them in the mailbox of each of them, and right, so to address them all simultaneously, I use this estimado, like dear, right? So the 5 of them. So yeah, in this group there were, I don't know who was Lucero, Carlos Castro, Sorin, and maybe who else?
And Rafa later.
Who?
Rafa Oribe later.
Rafa, yeah, and René Dagger, and Gemma, maybe.
Gemma, sí, Ana.
Anna was I think, but yeah, okay.
We are thinking with Lucero and the rest of Estimado. We hope in the next future we will have the Estimados workshop.
Estimados workshop.
We are planning. You will have news.
Thank you again, Jaime. Yeah, I mean, everyone knows Jaime, and everyone that knows Jaime knows that he is, a very distinguished individual, not only as a mathematician, but especially as a person. Yeah.
Thanks to you for your friendship and for all these years.
Yeah, I mean, you came I remember very well when René Letelier, a Chilean fellow.
Yes. I arrived with René later.
Yeah. I remember he told me, oh, there is a student, Jaime from Chile, he's coming. Would you like to mentor him? And I said, well, of course I can give it a try. And this is the result. So I owe this to René Letelier, that unfortunately passed away soon after that. So
yes, exactly.
To see how much you achieved. Yeah, he will have been proud. Yeah, very good. Thank you.
Thanks to you.
Okay, thank you, Jaime, for the talk. Well, we are finishing this session. If there is no another question or comment, I think that we will pass the word to. Well, I take the opportunity to say happy birthday, Enrique, and thank you for all your inspiring work. So very nice, and also I will give the word to Carlos Conca. Or Sebastian, maybe?
Can we make maybe 10 minutes? Because the free space starting at 4 Chilean time, so have a lot of time. We have 20 minutes.
Yeah. Okay, so we will take this time to go for a coffee or something, and in 20 minutes you will start.
Thank you.
Okay, we see you in 20 minutes.
Okay, we continue or no?
Maybe we can wait to Enrique.
Yes. Enrique is here.
Estoy aquí, lo que pasa es que tenía apagado el vídeo, sí.
Okay, thank you everybody for continuing with us. Carlos, you can start.
You are muting, Carlos.
Carlos. Carlos.
Okay, it's okay now. We are hearing me?
Yes.
Do you hear me? Okay, so the idea in this space is to make a kind of social or friendship tribute to Enrique with personal testimonies of life experience with him. We will start with Rodrigo, Sebastian, and myself, because we have prepared a special souvenir for him. Of course, we will not hand it to him personally because we are just virtually connected, but Sebastian will take this souvenir to him in his next trip to Germany. And before passing the floor to Rodrigo, I would like to insist on the fact that on the great importance that for our country, for Chile, to host this Congress. So many thanks to all of the speakers and to all of the people who has been chairman along the different sessions of the Congress. So, Rodrigo, I pass the floor to you.
Okay, thank you, Carlos. Well, Enrique, how I can say, thank you for everything, not only for the scientific issues, for the friendship, and for your advice. When I spend time in Bilbao with my family, I learn a lot of things with you. And how can I say? Sorry, Enrique, and eskerrik asko.
Gracias, Rodrigo.
Sebastián.
Okay, yes. So, Enrique, just a few words in addition to everything that has been said. Thank you for all your support during my young career as a mathematician. During my doctoral stay with you in 2015, even in that period of black light, remember, you support me to get ahead. I also thank you for allowing me to meet your beautiful family, Magali, Johanne, and Ainara. And I take the opportunity to thank them for sharing Enrique with us. In this short year as a mathematician, I can say that the support of the family is essential to carry out this journey. So one last sentence to celebrate your 60 years is due to our famous Chilean singer, Violeta Parra. And I say this word in Spanish, sorry. Que viva tu nacimiento, bello botón de rosal, por la voluntad del cielo, que vivas 100 años más. Thank you, Enrique, and eskerrik asko.
Gracias, Sebastián. Gracias. Eskerrik asko zuei.
So, together with Carlos and Rodrigo, we have this small gift for you.
You are singing a song. You are singing a song, the three of you. El trío.
No. Let me share my screen. So, this is a small gift for you. You see my screen?
Sí, qué bonito.
Yes, this is the Chilean flag and the Basque Country flag.
Ah, muy bonito. Sí, 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 muchas gracias. Muchas gracias. ¿Y eso lo vas a traer tú en el avión?
Así es.
Ya, ya, ya. Bueno, no has puesto ahí el bolígrafo para ver las dimensiones, pero se entiende que es de un tamaño moderado, ¿no? Que lo puedes meter en el avión.
Sí, 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 sí.
Vale, vale, vale. Muy bien. Oye, pues muchísimas gracias, muy amables.
No sé. And now, as I say, finally your family could not miss this day. Is Magali there?
Hi. Hi. Hello. Hi, everyone.
Ah, están ahí. Ya. Yo les estaba avisando de que vinieran para veros y resulta que estaban en el ajo, ¿eh? En el garlic, estaban en el garlic.
Yeah. Hi, everyone.
They were in the garlic. Yeah.
Okay.
So Magali, you start?
Okay. Cuando pienso en Enrique como persona y como profesional, solo puedo sentir amor, admiración y orgullo por su entrega, dedicación, compromiso con su familia y con la matemática. Desde 1985 que lo conozco, siempre he pensado que a él le aplica el verso de Pablo Milanés, cubano, nacido en 1943. Lo que brilla con luz propia nadie lo puede apagar. Para mí, Enrique es luz, tan brillante que logra iluminar a quienes lo conocen, respetan, entienden y saben quién es. Con tanta luz que ciega a quienes quisieran y han pretendido, con oscuras razones, temores y menosprecio, infructuosamente negarlo. Gracias a su sistemática perseverancia, la vida le ha regalado la oportunidad de conocer y compartir conocimiento con ustedes, sus compañeros de estudio, trabajo y dedicación en la búsqueda de explicaciones por medio de las matemáticas. Noble trabajo como nobles son todos ustedes por unirse a este reconocimiento, habiendo vivido en los últimos tiempos con cierta oscuridad, toda esta claridad que emana de aquí, de ustedes, es bienvenida y agradecida. Enrique, tu luz no se apagará ni en más de 60 años. Te amo.
Muchas gracias, esta sorpresa inesperada. Sí. Bueno, como dice Magali, la perseverancia y el grupo es lo que hace que... Bueno, pero eso ha sido, yo creo que esa es la definición del ser humano, en definitiva, ¿no? Si el ser humano es distinguido en la naturaleza es por eso, porque es capaz de coordinarse, de aliarse, de ceder y compartir para ganar más en conjunto, y también porque es capaz de cada mañana autoalimentar la fuerza que hace falta pues, para seguir, ¿no? Aunque solo sea por los siguientes. Para mí ha sido un honor compartir esta aventura también con Magali, por supuesto, y con las otras dos que están ahí, que me suena la cara, no sé ahora mismo de qué congreso las conozco.
A ver, Ainara, ¿viste algo ahí?
Hamasei urte bakarrik ditudan arren, betidanik ezagutzen zaitudala esan dezaket. Askok ezin dute berdina esan, baina nik sorte hori daukat. Zure eskutik ibili izan naiz beti, edonora joateko prest, hasten eta ikasten. Parkera pilotarekin jolastera edo Alemanian bizi izatera beti bidean zehar gidatu nauzu. Biok badakigu bizitzak ez dituela bakarrik izpialai eta argitzuak ekartzen, baizik eta haize bolada gogorrak eta ahotsak baita ere. Hala ere, zure alboan barre, negar eta oihuka egin ahal izateak pozik sentiarazten nago. Askok matematikaren arloan daukasun postuagatik ezagutzen zaituzte, baina ez dakitena da, aita bezala oraindik hobea zarela. Asko maite zaitu daita.
Qué ricasco, Maichia. Sí, bueno, como dice Ainara, Ainara cuando nació, lo primero que hizo prácticamente fue coger un balón y empezar a darle con la mano izquierda, ¿no? Y entonces a mí me pareció evidente que Ainara era zurda. Íbamos al médico y el médico decía, no, porque porque ¿no? Lo de ser diestro o zurdo se manifiesta, se confirma más tarde. Yo decía, joder, qué cosa más rara. O sea, para un matemático, en cuanto uno coge una bola 3 veces con la mano izquierda, ya se considera que es zurdo, ¿no? Y así es. Y desde pequeña Ainara lo que le gustó era el fútbol. Y efectivamente, muchas tardes, estuviéramos donde estuviéramos, lo que había que hacer antes de cenar o incluso después de cenar era bajar a jugar al fútbol, ¿no? Y entonces a Ainara le debo el haber mejorado un poco mis skills futbolísticos, que siempre fueron, digamos, de gama media-baja, ¿eh?
Bueno, y yo, aunque durante muchos años me expresaba más con las palabras, en los últimos tiempos recurro más a la fotografía y he hecho una pequeña selección de fotos familiares como aportación, mi regalo, claro que sí, por tu... por tu cumpleaños. Sorionak.
Eskerrik asko, Jana. Sí.
Mi amor.
Egoak ebaki banizkion, neria izango zen, ez zuen alde egingo. Egoak ebaki banizkion, neria izango zen, ez zuen alde egingo. Baina nonela, ez zen gehiago txoria izango. Baina nonela, ez zen gehiago txoria izango. Eta nik txoria nuen maite. Eta nik txoria nuen maite. Egoak ebaki banizkion, neria izango zen, ez zuen alde egingo. Baina nonela, ez zen gehiago txoria izango. Baina nonela, ez zen gehiago txoria izango. Eta nik txoria nuen maite. Eta nik txoria nuen maite.
Eskerrik asko, Jana, eskerrik asko. Muchas gracias. Muy bonita selección de fotos. Bueno, ya sabéis ahora que con las fotos hay que andar con cuidado porque luego te salen todas de repente, ¿no? Ollane nació en el 92, que fue el gran año, ¿no? El año de las Olimpiadas. Se celebraron los 500 en Barcelona, los 500 años del descubrimiento de América, aunque América ya estaba descubierta desde hace mucho, pero bueno, alguien llegó, ¿no? Cristóbal Colón llegó y entonces se estableció. Y me acuerdo que yo era, en la época, bueno, ha sacado Lucero una foto antes del 92, por ahí de esa época de la Complutense, y entonces en la Complu en la época había un rector que era, aparte de rector, era alguien pues muy capaz, extremadamente hábil, político también, Gustavo Villapalos, y entonces a Gustavo Villapalos, al rector, se le ocurrió que también iba a ser el 500 años de la fundación de la Universidad Complutense, y entonces, bueno, encontraron allá en Alcalá de Henares, que era el nombre, ¿no? Complutense era el nombre de la ciudad, a 30 kilómetros al al noreste de Madrid, Complutense era el nombre de la ciudad de Alcalá, pues encontraron un legajo de que, bueno, pues había habido en la época ya pues una escuela superior, un colegio o algo, y entonces con aquello se consiguió que también fueran los 500 años de la Complutense. Y ese año nació Ollane, y al ser la primera, pues se llevó lo mejor y lo peor, ¿no? Lo peor posiblemente porque fueron los años pues más activos, de más trabajo, de más viajes por mi parte. Viajaba en la época para 2 o 3 semanas, cosa que ahora pues ya nunca haría. Pero también se llevó lo mejor, y era pues que yo en la época tenía una fuerza que ahora evidentemente no tengo, y me acuerdo que cuando vivíamos en Colmenar, la bici que yo tenía, que todavía tengo, tenía una sillita atrás, entonces ponía a Ollane en la silla y nos íbamos horas a trotar en bicicleta por la Sierra de Madrid, que subía en la época sin demasiada dificultad. Y bueno, yo solía notar cómo al cabo de X minutos de rodar en la bicicleta notaba el casco de la bicicleta de Ollane que se posaba en mi espalda y se echaba unas siestas al aire libre fantásticas rodando, ¿no? Entonces, bueno, Ollane fue la primera y la que se llevó pues un poquito pues esos momentos tan intensos en los que también pues es cuando emergieron los estimados que decía Jaime, ¿no?
Bueno, los que quieran decir algunas palabras.
En fait, Enrique, la bicicleta se viene de esta época.
So in fact, so maybe I should talk in English because some people might not understand. So I am born in Eibar, and Eibar is, I mean, a small town in between San Sebastian and Bilbao in Basque Country, just in the middle. That was extremely industrial, and in particular, you know, even my father, before the Civil War, my parents were working in Orbea. Orbea is a brand that you might know. I mean, you can still buy Orbea bicycles, and they are exporting bicycles all around. Of course, nowadays there is a lot of competition, and there are brands that are much more prestigious, right, for the true bikers. But you can still find the Orbea bicycles is kind of a medium kind of quality level and price-wise. So, you know, in Eibar, bicycles, they were everywhere. So they were produced in the town. And despite of the fact that the town is quite hilly because it's in a very narrow valley, we were all used to you know, to bike, you know, to cycle since a very early age, right? And then for us, biking, it was natural to do it on a slope, right? So now when I go to Erlangen, I said, oh, this is the paradise. So this is all flat, right? So in Erlangen, nearly flat, you can bike, cycle, you know, we have done it in several directions, at least 20 kilometers in each direction. And that helps once one is not 30 anymore, but 60.
Yeah, but you were trained harder, so.
Yeah. I mean, but I used to bike. Yeah, we used to bike very, very heavy. Yeah, when we were younger.
Okay. Thanks.
So everyone willing to witness life experiences with Enrique can do it now in any language. We have enough people here to translate from Basque to English to Spanish to French, Romanian. So go ahead.
I must say, I remember with great pleasure when I went first to Benasque and discover the way you have managed to start this workshop with an improvised part and with mixing a lot of young and senior people, and with improvisation, and was you could be there very quiet, working hard, and very nice for interaction. And the food was great too. And so that's a very pleasant, I appreciated a lot. And also when I visited Bilbao, and also when I saw you in several other occasions in Paris, and it was great. And read the paper also.
Thank you, Fatia. So yeah, so Benasque was an idea of Pedro Pascual, right? So it was a Spanish physicist that unfortunately passed away, but he used to go with his father, that was a very fan of the Benasque Valley for hiking since he was little, and then Pedro Pascual became quite influential in the Spanish science system, not only as a scientist but also as a manager, and capable of, you know, building new centers and attracting funding. And the idea was his idea was precisely a place where you don't run a workshop on the traditional spirit of, you know, sequence of talks, you know, with a full program, but rather a place to meet, to enjoy collective work, and to think big, right, in the sense of exploring new topics, new ideas, and it worked, So
yeah,
I hope
it's a big success.
I hope we can go back in 2022, although things are not clear, right? It seems numbers are raised again. I mean, my friends in Chuan Zheng, that was with us in Madrid for a number of years and now is professor in Beijing, told me that numbers are even raising in Beijing, right, in Peking.
Yeah.
Chuan defined the process, you know, the policy that the government is developing in China, that is extremely strict, as you know, as trying to control to zero a system that is only approximately controllable, right?
Yeah.
He said.
Exactly.
Yeah. So, and I think it's everywhere a little bit the same. So, well, it's still uncertain whether we will be free to travel in next summer.
Yeah,
but,
it's not clear. I agree.
Hopefully we will. And yes, so Fatia, we are more or less same age. And I think we didn't meet so early because your PhD was in a different topic, I think in Lyon, right? With Denise, on nonlinear hyperbolic equations. But I mean, eventually this happened. And and we were so lucky then to share many trips and many experiences together, right?
Yeah. I appreciate a lot. Thanks, Enrique. And as I said,
to share with you a picture who was took in Cuernavaca. I'm sure that Lucero will have very fresh memories of that. We were there for a summer school with Gustavo Perla. And one night we went with Enrique to have dinner together. So I will share this. I have two pictures of this moment. This is one of them. Do you remember that, Enrique? Excuse me, do you see that? No, maybe
yeah, we see. Yeah. I think it's Nicola Burke and André Narbin, right? Is the
exactly.
Narbin, Gustavo, André.
And Gustavo. And on the other side, it is you eating.
I see. Working hard, right?
Working hard, yes.
No es choclo, ¿no? Era maíz, ¿no? Sí.
Maíz.
Sí.
We will see Gustavo tomorrow, huh?
Yeah, definitely. Yeah.
He's coming tomorrow.
Very good. Yeah, so Cuernavaca was, I mean, I think nobody forgets. Yeah, nobody forgets that. I remember very well. And I remember also jogging in the morning with Jaime, right? So, yeah, at that time, we still tried to be in good shape, right? Then later we abandoned at that time. it was a marvelous place, right? Hard,
Marvelous
far,
place, yes.
but far to get, but very, very worth visiting. I think this is the southwest
Southwest of Cuernavaca, yes. We were a little far away from the hotel.
Right. Yeah.
2 or 3 kilometers from the center, the centrum, the downtown.
Right. Yeah. I remember that. Yeah. Fantastic experience. And actually, I remember there were some people at the time, they were very young. For instance, I think people like Julio Rossi, I mean, they were the people that
Julio Rossi, he was there, yes, I remember.
So they were almost like students at the time, right? So then now
it was a simple school.
Yeah,
this was a simple school.
Simpa school, yeah.
Yes.
Yeah. And then I remember I also at that time I took the time of writing some lecture notes. I mean, they were published in this journal, Discrete and Continuous Dynamical Systems, and I mean these are efforts that are worth, right? Because then people use them, and so it was overall that was an extremely successful event. Yeah, I think there was also maybe Patricio Fellmer was involved in the organization, or I am mixing things maybe, or
I'm not sure.
Yeah,
Patricio Fellmer was involved in a Chilean Simpa school. South of Chile, in Temuco. This was in 1999.
Okay, so that it was before then, maybe,
This was maybe a little before, yes.
No, 7 years before, something like that. Lot of time.
In Valdivia, Carlos, no?
It was Temuco. University of La Frontera. Do you remember that?
University of the Boundary.
Oh, de la Frontera, yes, exactly. University of de la Frontera, yes. You gave a very nice course there.
Yeah, it was, at the time I remember it was done by slides, and I remember how heavy the luggage was, right? Because
exactly.
You have to deliver a series of lectures, it was a few, maybe, I don't know, maybe 200 slides or so, and that was kilos, right? So it could weigh a few kilos. Yeah.
I have here another picture. Do you see? This is Benasque.
Yeah, but this is more recent, right? Or...
This is quite recent, some 5 years ago or 6 years ago.
Right. So it was not the last one, but the before the last one or so.
Before the last one. So
yeah, I think probably
here,
I see John Barnes.
Giuseppe.
Giuseppe, yeah, I see. But I see John Barnes. Yeah, I see John Barnes there. I think John was maybe 97 and then 99, right? So
99.
No, sorry, 2000.
No,
2017. 2017 and 2019, right? So maybe this is probably 2017, I would say, right? 4 years ago. Yeah.
I feel that this is maybe the best restaurant in Benasque, no?
I mean, that's one of the, I mean, that's one of those we like the most. Certainly is, and it's in this small village, right? It's actually not, I don't know what is the name of this village. In between.
It is close to Benasque, not exactly
walking.
Benasque.
I mean, it's kind of 40 minutes walk, or I mean, it's a beautiful place, right? So, yeah, and I remember we had such a great dinner there. It was,
great dinner, yes, and really the wine was perfect.
Yeah, and then you have 40 minutes walk back, which is good for the digestion.
That's right.
Yeah.
Coming back was very nice.
Indeed.
And your smile here inspired us, our words in the souvenir, on the souvenir. Do you see?
What?
Your smile.
Yeah.
Smile in this picture.
I see. Okay. Yeah, I was happy that evening, definitely.
You was extremely happy, and this is what we wrote. Yeah. On the souvenir you will receive.
I see. Okay, very good. Thank you. So the souvenir is coming with Sebastian when?
With Sebastian, yes.
November 20, no? Sebastian, are you coming?
Yeah, 22.
22.
22.
We'll be there. We'll be there.
So I ask you
Carlos,
to turn
Carlos,
your camera.
cumpleaños. Que sé que cumpleaños hoy, Carlos Conca.
Sí, felicidades.
Muchas gracias, Magali.
Un abrazo a toda la familia.
Un beso.
Y un abrazo
Ollane,
a
un
todos
beso.
familia también, ¿eh? Que ahí está mi
Ainara,
mi-
un beso, ¿eh?
Sí.
Igualmente.
Rafa, qué bien, Fatia. Ay, qué bien. Muchas gracias a todos. Un abrazo.
Gracias.
Les pido si pueden encender su
Magali, it was nice.
para sacar una foto. I ask you if you turn on your camera to take a picture. And
Oh, yeah, these puzzle global pictures. Yeah, that's a good idea.
so Rodrigo is the photographer.
Yes. Okay. Okay, I will take a picture now. Okay. No other. Okay, it's okay.
Y aquí yo encontré una foto, la única que tengo. ¿La muestro?
Of course.
¿Dónde está? ¿Dónde está? Se me perdió. Bueno, trató el desktop porque no la... Ay, eso. No está muy buena, pero... Fue una vez que
Eso es en Bilbao, eso es en el Hotel Ava, ¿no? Que hicimos el workshop ese, ¿no? Sí.
Parece.
Sí, que estaba, me acuerdo que vino, sí, veo aquí abajo a Magali, a César, que era nuestro gerente, Alejandro, Felipe. Estaba también, vino Figali a dar, veo aquí Miguel Escobedo a Corón también, que Jean-Michel y la donné en cours, qui était fantastique. Et il y avait Miguel aussi, mais il y avait Figali aussi qui est venu donner un cours. À l'époque, je ne le connaissais pas, il était tout jeune. Voilà, ça a été un bon investissement de le faire venir. Hein. Voilà. Et c'était ici à l'hôtel là-bas et j'ai un très bon souvenir de ces cours, en effet. Ça a été très dynamique et très réussi et des cours de très bon niveau. Voilà.
Sí.
Gracias, Axel.
Gracias a ti.
I have here a surprise for Ainara. Is Ainara there?
I'm here.
Sí.
You are there? Ainara,
Yes.
¿estás ahí?
I am.
I have a surprise for you. I will share screen.
Eso me acuerdo, sí. Sí, sí.
And this one?
Sí, 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 me acuerdo. Que
This is the best.
Yeah. I remember that.
I think that Ainara was too small at that time. He was.
I think our Wi-Fi. Oh,
Yeah.
there. Oh my God! I remember this. I remember this day.
Yeah. Yeah, she was, I think we were discussing on the blackboard, Carlos, and then she was reproducing the same
The
things.
Laplacian and all the
rewriting everything she was
mathematical operators.
Yeah, down there, right? Yeah. At the time, maybe she was like 4 or 5, right? Yeah.
4 or 5, no more
maybe
than that.
2000, maybe it was 2000, 12 or so. 7 maybe.
7 maybe.
I think both of us have this experience of drawing in the blackboards while I was working.
Of course.
I remember that as well.
Qué bueno se oye.
Rodrigo, you have a picture also, no?
Yes, I will send. Give me a moment.
Ah, que lo mandaste al...
Sí, ahí está.
Ah, esta es la foto de grupo, excelente. Muchas gracias.
Ok, gracias. Gracias a todos por participar y por quedarse hasta tan tarde y por toda su disposición a realizar este congreso online, que bueno, de una u otra manera lo hemos podido llevar a cabo. Nos queda el último día de sesiones, así que gracias a todos por participar.
Gracias a vosotros por haberlo organizado también y como dices, a todos los que pacientemente han estado ahí todavía incluso a las 8:31, que aquí ya es la hora de, ahora ya es la hora de la caña.
Oye, yo me he conectado a las 6 de la mañana, Enrique. Es peor las 6 de la mañana que las 8.
¿Por qué a las 6 de la mañana?
Pues porque aquí son 3 horas menos que en Chile, 7 horas menos que en Europa. Y empieza a las 6 de la mañana.
Es verdad que hay un gap todavía mayor entre Chile y México, ¿no?
Sí, sí, sí.
Ya,
Entonces a las 6 de la mañana aquí he estado.
Pero ¿y por qué hay tanta diferencia entre México y Chile? Eso no está armonizado todavía los horarios en
No,
Latinoamérica.
porque es el horario de invierno en México, cuando es el horario de verano en Chile, y entonces se hace un gap muy grande. No es
Sí,
una
porque
hora.
no hay tanta diferencia, ¿no?
No, es el cambio de horario que van en sentido contrario en esta época del año.
Porque si uno estando en Santiago mira al norte, cuando llega a México, ¿qué se encuentra? ¿Qué ciudad se encuentra al norte
Yo creo
de
que por Mérida, por ahí, Yucatán, la península de Yucatán debe ser más o menos.
Muy bien.
Pero no
muy
es
bien.
tanto eso, sino el horario de verano y el horario de
Sí,
invierno.
claro, es verdad. Es el hemisferio. Efectivamente. Pues nada, muchas gracias, Lucero. Y bueno, pues ya, ahora ya puedes ir a la oficina tranquilamente, ¿no?
Exacto.
Ahora puedes empezar a trabajar ya sin que te moleste nadie, ¿no? Porque claro, como son 7 horas menos, tienes toda la tarde por delante, ¿no?
Claro, claro.
Así que ahora
¿Qué crees?
ya empieza lo bueno. Muy bien.
Sí,
Bueno,
sí.
pues un abrazo. Gracias por
Bueno,
estar ahí.
felicidades, Enrique.
Walt, pronto.
Un abrazo a todos.
Felicidades, Carlos, por tu cumpleaños.
Felicidades.
Gracias.
Felicidades, Carlos.
Adiós. Que estén muy bien, ¿eh?
Felicidades.
Hasta mañana, tempranito.
Gracias, Alberto. Hasta luego.
Gusto verte, Magali. Chao.
Saludos,
Gusto, ¿eh?
Magali, Ollane, Ainara.
Chao.
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 Verlos pronto a todos.
Chao.
Chao.
Gracias.
Gracias.
Chao, chao.
Hasta luego.
Hasta luego.